Okay, hello everyone again. So we'll go back on Grayscott today with wizardry with C++ this morning and a bit this afternoon, and then we will talk about profiling. But we will start a bit with profiling. So I will start with a brief lecture, really small lecture, just to give you an overview of what we'll do. And of course, after that, we will play with everything because it's the goal of the lecture. So if you want to start to get some stuff before I start, so you can get to the program normally here. And then if you go to the container list, if you want to follow with the container, you can get this container here. So normally everything will be interactive, so you don't really need to get the job image. Normally you get an interactive image, it's okay. So one of these, depending on your favorite containerizer, of course. If you want to follow in must, you can jump here on Kubernetes. If I do that, you will have a sign-in. So you put your login, your password you get with the paper Mo gives you yesterday, and then you select Grayscott 2026, and you select performance with Stencil in C++. And then you start your pod, and it will be useful for a bit later, but everything will be okay. If you want to use Pixie, maybe some people want to use Pixie in the room here? No? No? Okay, it's nice. So I have good news for Pixie. We'll do a bit of magic with Macao today, and the good news is Macao is on CondaForge. The bad news is CQA, one tool that I will use for Macao today, is not in CondaForge yet. So you have to pick Macao directly here. If you want to follow with Pixie, so you get here macao.org, you get download, and then you pick the one you want for x86 or Arch64, depending on your architecture. And okay, yeah, of course. This one? Better? Okay. This one? Okay. Yeah, I'm pretty sure I will have to do the same, or maybe here, not, maybe here, yes. So, but that's horrible. Yeah, that's always horrible with the pad. So I will try to do this kind of stuff. Should be quite okay. Okay. So, of course, if you have some question, don't hesitate to use the Discord. So normally, if I manage to get already, I didn't start yet. Come on. For those who don't have must, what should we do? Yeah. So if you don't have must, you can pick container here, or you can get the bare metal installation with Pixie, but you have to get Macao on the side. Otherwise, you will have a problem for the last part of the lecture. But normally, you pick the container, you have everything, including Macao in the container. Just for Pixie, it's a bit broken because of CondaForge, but just that. The containers are not really big, so if you get them at the last moment, it's not a problem. But if you prefer to get everything on time, it's you can do it right now. And normally, if I remember well, I should have a lecture C++ courses, and so I will put here. I will put all the link and all the command, because of course it's still used to type commands. So I will give you the command during the lecture. So let's introduce a bit this topic. So as introduction, we want to explore a bit some stuff here. In terms of computing with the Grayscott reaction, as was presented yesterday. So we'll do some function timing, so how to time a function, what are the problems with the function timing. So I already showed you some problem yesterday with the compiler, but we will continue today, of course. Some benchmarking, some data layout, vectorization, Laplacian, so you can have several ways to write the Grayscott, so we'll explore the several ways. And with the simulation, so basically I get my main Grayscott for the full lecture. And of course, maybe if you want to get all the word detail of the lecture, you get this lecture here. So if you go in the container and you jump here with this link, you will get this lecture. So it's a really long lecture, so I will not dive into all the detail here. But if you want to know more, to get all the command, all the information, you will get everything here. But it's a 700-page lecture, so of course we'll dive into it in 2 hours and a half. So the point here, it was a bit of a challenge for me. It was to write all the performance tests with one main, because it's funny. So I have one main here with a bit of design, of course, and then we get some argument parsing. So I already said to you in the webinar that's a bit tedious. So of course you do it once and then it's okay. Some I/O. So here we will pick HDF5 to produce the output of the simulation, which is quite common in simulation, in fact. So let's do it. And the final part, of course, the part for auto-vectorization, for example, but of course we'll have some blocking, some advanced blocking for this afternoon, some TBB, some NVC++, and CUDA, because of course I have the same design for everything and it's working. So so we'll explore some of them, and that's really flexible. So of course, if you have you want to use another technology, you just change the backend and that's it. So you don't have to rewrite everything, and that's of course what we are supposed to do as developers. So let's pick an ADAMR product just to start, because of course it was one of my lectures, so we'll start with an ADAMR product. So it's an element-wise operation, and you can have a for loop like this to express your computing, nothing really fancy. And if I want to time my ADAMR product, I will initialize the table and freeze the table, as I showed yesterday, and then I have to call the ADAMR product at some point. So I start the timer and stop the timer, and the precision of the timer is nanosecond and cycle, depending on the timer you want to use. And sometimes they disagree, and it's important also to have this in mind. And generally what we do is we loop, we do several calls to have more precision and get more precise results for the end. And then we can compute the elapsed time, the real elapsed time, thanks also with respect to the number of iterations you did for the call of the function. That's really basic, and we'll start with that. So you get the total time, the time per element. It's always nice to have the two metrics, because of course if you increase the number of elements and your computing time is decreasing, something is strange normally. So it's nice to have the two elements. And with the time per element, we'll see the nice plateau I showed you yesterday for the cache. So it's quite nice also. So if I get the ADAMR product in O2, I get this kind of stuff. So it's 10,000 timing. So sometimes it's not really precise. A lot of spread here. Sometimes you have some trouble. Of course, there is an accident. Maybe here could happen. Maybe the system was busy to do other thing, and I break my timing. But most of the case, it's okay. So of course, once you do some profiling, you want to have a nice Gaussian distribution, because it's so nice. You have a nice standard deviation, you have a nice mean, and it's nice to understand. But of course, it's not really like that. We have this kind of stuff normally. So it's a multimodal distribution. You have several distribution into the same, of course, because the CPU will do what he wants to do. And of course, sometimes we fast, sometimes not. Sometimes you are fighting with multi-threading, as Sebastian mentioned yesterday. Sometimes not. Sometimes it's okay. Sometimes we're waiting for I/O, sometimes not. So quite complex distribution. So here, of course, the mean makes a bit of sense, because as a user, we'll see the mean, but prefer normally to use a median instead of the mean, even if the mean makes sense at this point. But don't use standard deviation, because of course standard deviation means nothing, because here you will have some problems. So quartile or quantile in general is better. So quartile, decide whatever you want, will be better to compare, to have the error bars of your performances, of course, because it's quite common once you want to do some timing to have performance error bar. Because if you have one performance and that's it, we cannot conclude anything. So it's important to have several points and then error bar on the points to be sure that everything was okay. So what is vectorization? As we mentioned yesterday, the point is really simple. You have several elements, you compute it at the same time, and that's it. Depending on the architecture, it will be quite okay. So in terms of vectorization, if I get my example in AVX, I will have the border of vector register, and then I have aligned data. So we'll talk about that also today, and I can get my vector here. I have align data, and in I compute my vector computation, and in 3 cycles. So if we according to this plan, we'll say, okay, 1 cycle per vector computation. Could be less, could be more, but let's assume it's 1. It's simpler for the slide and to understand the meaning of it. It's okay. Sometimes you are unlucky, you don't have aligned data. So here the problem is I can vectorize the 2 vectors here, no problem. But here I have what we call a peel. So I will consume element 1 by 1 to get to a border of aligned data. And then I have the tail. And again, I cannot fit a vector register here. So I have to consume element 1 by 1 at the end. So here it's scalar computation only. So of course it costs a lot. 1 cycle per element here. And it's 1 cycle per 8 elements in the vectorized computation. So of course it costs a lot compared to the size of the vector register. And it will be 10 cycles. So here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Too bad, a bit bad. So what we do as a trick, because of course life is not only composed of values with a multiple of size of a vector register, because we are unlucky as data scientist or as developer or as a HPC programmer. We'll use a padding generally to be sure that, okay, it's not a multiple, but we'll put some padding and it will be okay. And then in 1 cycle, I can compute my 3 elements here with some crap. The value of the padding is important. So normally you want to use a neutral operation for the operation you want to use here. So mainly 0 if you have addition, subtraction, multiplication, stuff like this. Of course, for division, you will have some problem, but the division costs much more than the others. So normally you prefer to multiply by the inverse. So 0 normally is quite common, but be careful if you don't have 0 for whatever reason, because you divide, you will have 1s, for example. So here with the padding, we drop down to 8 cycles, which is not so good, but better than before. But the vector is very short, of course. So at some point, it's important to have that in mind. If you put too much vector, it's nice because you will vectorize a lot, but maybe you will get out of the L1 cache, so we'll have a problem of memory after. So that's a trade-off. You have to play with it to be sure that everything is efficient. So if I get my Adama product vectorized, so as I showed yesterday, but with more color and with more error bars, so I get my border of L1 and L2 cache, as we mentioned yesterday. So here I read my data really quickly, and here it's more quickly because the cache is a bit bigger, but a bit slower also. And here I have a nice step, and with the Adama product, by definition, it's memory bound because we have only 1 operation for two read and 1 write, so memory bound here. So of course, the step is really nicely highlighted. Yeah, okay. Not in the C++ course, or Carolina said, I'm struggling to understand how the second example gets to 10 cycles, like 6. Okay. Here I don't have a vector register. I cannot use this data because maybe it's not the data I want. It could be my data because normally the OS will give me some pages, but maybe it's another table here. So I cannot say, okay, I can just cross the value here for whatever reason. So I have to consume this 1 per 1 because a vector register will compute for the full vector here or full vector here. So here I cannot. So I have to consume 1, 2, 3, 4, 5 cycles. So for 1 operation, because 1 operation, as I mentioned before, 1 operation for 1 scalar or 1 operation for 1 full vector register, it's the same cost. And here, so it's 1, 2, 3, 4, 5, 6, 7, and here it's the same, 8, 9, 10, because I cannot consume the 3 at the same time, because here I don't know what I have, if I don't have padding. So that's the answer. So I was here. Normally it should be okay. Nice. Carolina is happy. Okay, let's move on. So with the Adama product, so I have my steps. Normally, if I have my step, I'm happy because it's quite okay. Even if O3, so remember, it's a partial vectorization, but I still have a step. And the question is, what happened if we use less and less elements. Because generally, everyone is tricking you and say, okay, let's start with 1,000 elements, and then we have a nice step, and that's it. What happened? Do you have an idea of what's happening? First question of the day, of course, but Macao doesn't count. Any ideas in no, not yet in okay, maybe we can move on a bit. I use less and less elements in my register, so I can get this kind of stuff. So here I use 1,000 elements and 110 and 1. And I get this kind of conversions here. And the question is, what is it? Come on. What is this value? Of course, there is a big problem with vectorization here because I asked the vectorizer to vectorize, but there is only one element, so come on, there is only one vector register with one element. So yeah, with a micro, yeah.
So how do you actually time this? Because timing is crucial in this when you get to not one element per se.
It's the same as before, just you have a lot of calling of the function. So you remember, you get the Adama product, you put it in a loop to call it several times, and then you time it.
But what's your first? How is your timing, and do you wait for the result to be computed before you actually time it?
Yeah, I wait for the result every time. Yeah, otherwise I will not get this one. I will get the crappy one as yesterday, once everything fall to 0.001 nanosecond, something like that per element. So here I compute, I get the result, the compiler. Yeah, with a micro, yeah.
Does this mean that there's no more pipelining since we only do it once? It just does all the cycles once with overhead?
Yeah, that's it.
Okay.
You are really close. So here, I don't have the focus. Yeah, okay, come on. So here is the pipeline length of my CPU on my laptop. So I pick the documentation of Intel, and it's 14, 15 cycle. So this is kind of measurement you can do on your laptop if you don't really know the size of your pipeline in terms of cycles. As Sebastian mentioned yesterday, you get the pipeline, and of course, if you put one element in the pipeline, you pay the whole pipeline for the computing. And that's a trick you can use to reverse engineer the size of the pipeline of your CPU if you are curious. So you can really diminish the number of elements, and then you will get this kind of stuff. And that's also the point here. I said before that, of course, if you increase the number of elements and you have a better performance, it's quite strange. This is the case here because I have really few elements. But nobody is showing you that before, but that's a kind of a nice trick you can use. So CPU pipeline, as we said yesterday, you have instruction fetch, you fetch the instruction, then you decode, then you execute, and then you do some memory access, and you write the byte. You can do the opposite and say, I get the memory and then I execute. This is the same stuff. This is the same idea. So 5 steps. Of course, now it's much more than 5. It's 30, 40 more than, or sometimes 80 or so, depending on the architecture. But 5 it's okay to understand that. And of course, I have the pipeline net here. And if you get the documentation, it's 14 stages for Intel and 15 stages for AMD. So stages is cycles. They don't get the raw detail inside the stages, of course, because it's a proprietary knowledge. So they speak about stages, but all the stages are split into small pieces, of course. So here, if I decode the previous instruction, for the same time, I decode the end instruction, I can fetch the next one and the previous one, etc., etc., etc. And at some point, I get a filled pipeline. So here it's really efficient. And here I can perform five steps at the same time. Of course, if I have only one instruction, I have to go to the pipeline alone, and that's it. So not really efficient, but you get the size of the pipeline with this kind of trick. Okay, So in terms of layout, can get also this one quickly. It's a reminder for yesterday. So if I write or read some lines, so one cache line in 64 bytes, and if I have an array structure here, 80 bytes, I'll get this kind of stuff on my memory. So the red block are the structure, and then I get my sector in white. And if I have a thread and I say, okay, let's read U, for example, I will jump from sector to sector, and of course I will kill my performance because here I will read 4 bytes out of 64. As Sebastian mentioned yesterday, that's really bad. You don't want to do that because you will always fetch data and you will kill your performance just reading data that you are not using, of course. And putting data into the cache has a cost, even if it's really fast, it has a cost. And if you do it for nothing, it's a bit problematic. So you want to do some SOA, so structure of array, and say, okay, no, I want to have a table of U, table of V, table of W, etc. And then I have everything contiguous in memory. So of course I can vectorize, otherwise it's not possible. But here, with 2 sectors, I can read the full values of U. And if you want, of course, to use U and V and W, but not the other, or mixing, something like that, and not everything, it's better because, of course, you don't have to read everything and to jump in the memory, so it will be much faster. And of course, you can vectorize, otherwise you cannot. So nice also to have that in mind. So here, I use all the bytes I drop, I read in the cache, so everything is efficient. That's important also to have that in mind. So the key topic here, use tables, use arrays, stuff like this, but never pointers of pointers of or really complex structure. You will kill your performances by construction, so you don't want that. So in terms of read and write, that's a bit the same. So you still have the same cache size, and if I have a thread and I read contiguous data, it's okay. If I have a read and write, I have 2 threads, they are contiguous to each other, it's okay. Nobody is bothering the other, it's okay, no problem. If I have 2 threads and write the same cache, of course, they will fight in the memory to get the same information, and you will kill your performances because you don't have any more multi-threading, or you have multi-threading, but with 1 execution at a time, which is a bit of a pity in this case, and the same for the rest. So again, I bothered you for all the webinars. I will bother you again. Express parallelism to be sure that everything fits well in the memory. So if I have some events, independent event, because as Vincent said yesterday, it's not embarrassingly parallel, it's deliciously parallelized, because of course you want to be in this case because that's the only way to scale properly. So of course it's it's less classy, but it's really efficient to do that. So if I get some event, I want to express parallelism, and maybe my events are really big. Can happen if you have big detectors, stuff like this. One event could be really big, and maybe you cannot put enough events in your memory to have enough threads to run with them, especially on the GPU side, but we'll see that next week. But of course, if you think that for the very beginning, for the CPU, it will be really simple to go on the GPU after that. So maybe I have to break down my event into pixels. I have some captors. Let's say it's pixel, could be capacitor, could be whatever you want. The same idea. And maybe it's still not enough, especially on the GPU. Maybe you want to start much more threads, so 700,000, something like this. So let's break down again the pixels into slices, waveforms, pulses, whatever the time response is of your captor. And then you have a big tensor. And the question is, what is the ordering of the axis I want to have on this tensor? So, okay, so I have to ask myself, okay, what do I want to do with my tensor? What is the order of the steps of the analysis? So first, let's pretend we'll use some calibration, which is quite standard, in fact, in data analysis. So you have tensions, you have voltages, and you want to pick energy, number of photons, stuff like this. So to be able to compare all the pixels together, all the captors together. So let's pretend for this that we will use one tiny block here, and regardless of the ordering. So regardless of the ordering means you get the same performances and the best performances possible if you change the ordering. Of course, if you kill your performances by changing the ordering, this step is supposed to be done in a certain ordering. But if it's not, let's pretend it's not for this one. I get all the best performances, so basically the calibration does not care. So here could be a calibration with the scalar, could happen. Why not? So let's pick the second step. So here it will be an integration. Integration, so means I will sum my slices, so do a reduction. So every time you heard about reduction, you heard about some things about back dependency. So I will have to wait for the results to be available to sum, as I showed you yesterday. So waiting for the results, it's a waste of time, of course. So you don't want to have these values and this value contiguous in memory. Otherwise, of course, you will have one computation. You will wait for the computation to be ready to finish the computing. And of course, you don't want that. So obviously, if we don't want this axis and we still want the data to be as close in memory as possible, we'll use this axis as contiguous data. So after that, you can say, okay, row-wise, column-wise, depending on your language, of course, but here it will be the axis of contiguous data. So here I can vectorize, I can GPUify, no problem, and it's okay for the integration, and it's okay for the calibration too, because the calibration does not care. So nice. Then once I compute, of course, I want the second line to be not too far in memory for the first line, because if I finish to read the first line, normally the CPU will be a bit smart and try to fetch data after that to be sure that if I want to continue reading the data, they will be already in the cache. So it will be really fast. Of course, if you have pointers of pointers of pointers with multidimensional arrays, you'll kill your performances because the next line will be not contiguous in memory, and you will lose some time with that. So the next, so second axis here, if I develop in C++, if I'm row-wise, will be this one. And of course, the first one, the larger axis, will be the event here. And I can parallelize on node, on cluster, and on GPU, but it will be, of course, for the next week. So computing drive data storage is really important. You cannot say, I will store my data this way without knowing what you want to do with your data. You have to have the knowledge of what you want to do. You can use tables, but even tables, you have to get the nice axis. If you have vectors, it's okay, because of course you have a nice, yeah.
Yeah, I saw other people wondering in chat, but are these terms pixels and events generic terms, or is it tied to a specific computation?
It's here. It's could be in astronomy, stuff like this. You get some images from a telescope, and then you have event, and then you get some pixel in a camera, this kind of stuff. But okay, it could be a capacitor for Atlas, for example, for particle physics, and then you have you get some energy in particles, and then you get pixels, but the pixel in 3D if you want. So that's the same. You have a captor. Just a captor. Okay, so that's time to play a bit with everything. So Macao. The goal of Macao is to have a tool. So you have a mode like Valgrind, but I prefer Valgrind, so I don't use it. But there is a CQS, a code quality analyzer. So I talked about a bit yesterday. Really quickly. So the idea of the code quality analyzer is to analyze directly the binary produced by the compiler to check if everything was done well. So if it's properly vectorized, if you don't have too much back dependency, what can you do to improve everything? So that's a really nice tool, and of course I want you to play with it right now because it's really powerful. So the idea is to use it. So Macao CQA and then FCT loops. You get the name of the loop. Of course, it's working only on a dynamic library, so SO. If you have A, it's not working, so you have to compile it dynamically. But if you do that, you will have a report, and Macao will tell you, okay, you have this amount of vectorization in your function. You will have, you can do this and that to improve it. You can do this maybe you can use this option or this particular compiler with this option to get a better result, or you can remove the back dependency of your computing. We will have plenty of information with that. And so let's try. What? It's too fast. Okay, yeah, okay. So I will give you here, take your time. So Macao CQA output format HTML. So here it's to get an HTML output. So I will do it, I'm pretty sure I will do it several times. So we'll get everything. So if I do that and I do Jupyter, where is my Macao here? And since it's loading, I can, so here I can give you, well, let's start with the first one, of course, this one. So the ID, if I'm here, I'm going in, I don't have any build directory anymore because I killed my build directory. Okay. It's going to build directory. Are you happy? Yes. So I can compile everything. So it's static analysis, so it's not a problem if you are a lot on the same machine. We will not run anything for now. We will run some stuff after that, but not for now. So here, so normally you should be okay. Okay, nice. So here it's the same. So if I go, I'm pretty sure I don't have, this one, yeah, it's okay. I need to have some space to type at some point. Okay, let's pretend it's okay. So I get in my build directory, I do, no, not you, yeah. So, so I explained that also in the demonstration. So I use an alias, which is a CMake Phoenix, to get all the path to be sure that CMake will get the information inside the Pixie environment. So if I show you that, normally, yeah, you will get CMake so the parent directory, CMake install prefix, CMake module path, and the CMake module path is important to get the Pixie env Grayscott share CMake modules. That's a trick to be sure that Pixie will be happy. And I can do, I think it's 64, but no problem, it's okay. So I compile everything. Of course, if you prefer Ninja, you can use CMake -G Ninja with capital S and capital B to get the build directory as you want, so no problem. I prefer to use it this way, but of course you can do everything you want. It's CMake, so no problem. And you get, of course, here in the README some step to compile. If you forget what I just said, it's okay. Pretty sure. Yeah, you have the command in the document. Not all the command, because I did not want it to spoil too much, but to build everything, you have the command. And then we'll do it together to be sure that everything is clear. And so basically, well, I will do the two, I think. I will do this one to show you the nice report of Macao here. If I do that, okay. So here, if I pick, where are you? Here. You should be here. I go in build directory, and here I have some Macao report. So once you use, or maybe I will use this one. Once you use Macao and CQA, you can use output format and say HTML and output path, and with a directory, with a non-existing directory. Otherwise, Macao will bother you a lot. And if we do that, you will have a nice HTML report, and I will show you that right now. So we'll get this kind of stuff. So you have everything about the function, the only function you ask. So you get everything. And then, of course, that's the first example, so nothing is really done the best way possible. So it will say, okay, 4% of the peak computational performance is used. That's a bad news. It's too. Okay, okay. Shadow panel. Go wider, please. Okay, so here I have 4% of the peak computational performance. Of course, it's a shame. Of course, I want to do better, and of course, I want to get some advice. So here, you will get some information, and you will have some panels. So we'll have everything here. So some details about what's going on, some potential. So maybe there is some addition and subtraction. Of course, it's a Grayscott kernel, so I have some subtraction because I get my Laplacian. I get some addition because I add the contribution, this kind of stuff. So of course, I have everything. And here you say, hey, maybe you can change it and get a FMA, as we mentioned yesterday, fuse, multiply, add. Yeah. Oh, I forget to put it in the chat, maybe. That's what you are doing? You are telling me this with... I do too much thing at the same time. Okay, here. Or maybe in question for teacher and in C++ courses not to have some noise. Yeah, maybe C++, it's meant for that. So if I do that, you get the full command, so you don't have to be bothered with all the paths. But basically, you can pick a library or a program and say, okay, I want to get this function. Of course, the function has to exist in the binary. And then Macao will analyze this function and the loop inside the function. Of course, if you don't have loop, Macao will be really sad about that. But you should have some loops. If you have also some condition in the loop, some branching, stuff like this, Macao will analyze all the paths possible. And if there are too many, Macao will bother you and say, there are too many paths, so I cannot analyze that. So it's can also happen sometime. So again, output format, compute output path, and then the loop you want to analyze and the library, the binary you want to get. So here it's a test binary. It's not it's an executable. It's not a library, dynamic library, but that's the same idea. And of course, this is a nice output where you get a lot of nice results. You have some hint here. So maybe we'll say to you, maybe you should permit loops because, of course, you can have a better way to walk through your data. So I'm pretty sure Sebastian will show you this maybe this afternoon. If you change the stencil, you explode the stencil and you pass through the loop in a different way. So also, Macao doesn't have really the information of if data are aligned or not. So maybe you should align your arrays, maybe not. So on 32-byte, because Macao detects that we are on AVX2 here. So if it's AVX 512, we say 64, but here it's 32. It's okay. And then we get the expert part, but maybe we'll check that a bit later, because here, of course, everything is really bad because we don't have much vectorization, stuff like this. So we'll see that a bit later. And if you are using this, and you don't want to be bothered with VS Code because it's not really simple to open an HTML in it.
Pierre?
Yeah.
Can you put the full commands to get up to this point in the chat, because some people are trying to follow.
It's in the chat.
Yeah, but you put just the macro commands and probably the one before.
Okay, so I will pick the command in my bash because I don't remember this kind of stuff you mean.
Yeah, thanks.
Okay, so you have everything. So it's reverse order, but so basically you go in the example, you create a bit directory, you compile. Yeah. The CMake file?
Yeah, and how to open the report to the
That's the problem I wanted to show you. So you can, but it's really annoying, and I managed to make it work, but it's quite not that good. In fact, you have a plugin with a live server inside VS Code, and you are supposed to be able to have a proxy to connect to it to get the HTML report. It works once. Not really sure that it will work on Jupyter Hub because, of course, everything is under control and you cannot have a proxy like this. So the other way to get the information, that's what I have a simpler command here. I will put in the chat, of course. So if you don't want to get, and generally it's quite nice also to have this command also. So you don't have the HTML reports fully. So you don't have the nice interface here, but you get all the information. And what you will get here, if I call this command, please, yes, past, of course. Yeah, so if I make some room here and some room here also, should be quite nice. Nice. I get the same reports, but in text. So you get all the information. With a bit of habit, you will get to all the information really quickly. And if you get some highlighting also, it will be even quicker. But yeah, once maybe you are on a other server, you cannot access to a web server, stuff like this, and you want to get the report and you don't want to be bothered with another stuff. So here you get exactly the same information, but without the nice HTML stuff and the nice tabs. So here you get the information. So it detects my architecture. Of course, it's not exactly the same. And then you say, okay, the source file is this one, because of course it's better, really important once you compile. So it's done automatically in the CMake. If you compile, it's better to have the debugging symbol. Even if you are compiling in 3 or fast or something like that, always use debugging symbol for Valgrind, for Macao, for all this kind of stuff, because they will give you all the information and say, okay, this function was defined in this file, and then you can pick exactly what is nice, what is wrong, and that's really faster to get information. So here, so Macao detected line 77 in this file, what I just said, so the line, so maybe I can jump. Don't remember this kind of stuff. Yeah, of course I have less room now. So 77, this one. So you get this this function here. So I create my I have my parameter. So I create so I have the restrict keyword, the famous restrict keyword to be able to vectorize, and then I loop over all the rows, and then I loop over all the columns, and then I apply my stencil here, and then I compute my stencil, and at the end, and of course, line 77, I get this kind of stuff. And here you can also see some tricks. Here the optimization is not that good because I didn't use really hard optimization flags. At some points, this line will disappear. We'll remove the loops at line 77 because the compiler will see, okay, you enroll, but you have a session 3x3, hard-coded because I put in the loop 0 to 3 for the indexes, and the compiler see that, of course, the loop is really small and it will unroll it for me. So no more loop here if you ask Macao and you say, okay, the loop disappeared. No, the loop was simplified by the compiler. So that's a trick of yesterday. Is everything okay right now? It's clear? Maybe I should see. Yeah, but 25, but So there is another C++ lecture channel somewhere? Question. Okay, CMake.
I think Pierre put everything in the channel, the command channel for the teacher. I mean, it's better.
Yeah, but
Probably.
it was to not be too noisy about that, but of course maybe it's will be more simpler to follow. So if I put that, okay, and or maybe we can start with that, and then I will get this one first, and this one second. So we'll get everything in the same channel, but maybe it's simpler for the question also. So you have the output with the HTML, the output without for the first one. And then in your build directory, you will get the report, or in the terminal, you will get the report if you use the second command. Is it okay for you? Yeah? Okay. That's the first command, so. So here, to give you what's going on, okay, 4% of the peak performance, not that good. Of course, we can do better. So let's try another target, so this one, to see what's going on. So I will put that also in the chat, so I'll get this one. So here it's auto-vectorized, so I ask the compiler to auto-vectorize. Here. So you get the HTML in second and the light one in first. So if I get this one, maybe you'll see what I'm telling you here. So give me some room again, please. So here. And maybe we'll do the same, so you will have a nice report. So all the names of the report are different, so they will not fight to each other to get the same directory, so normally it's okay. And if I do that, so I go out of this one, I get into this one here, I can remove this one also. So it's better, 6%. Way better than before. Yeah, I'm waiting a bit because this part is really important. So tell me if it's okay for you. Sur batterie, non.
Pierre, there are some questions about Aptainer with your bash RC.
Yeah, I never had to source the bash RC for Aptainer. I'm not sure, but Isabel get the same behavior. I don't know why. But sometimes, maybe it's related to the version of Aptainer, I don't know, but sometimes you have to source the bash RC inside the Aptainer, inside Jovian, to get the Phoenix CMake command. Or you can also pass, get the full, or maybe I can put that to you also, it will be more clear. Okay, give me some room also. That's too big for me, in fact. If I get, where are you? Yeah, this one. So you can, maybe, that's the same. If you don't have the Phoenix CMake command, you can use this one. That's the same, in fact. We'll get the same information, and it will work. So that's a bit longer, but normally it's okay. Yes, I need to think about that, but yes, it could be possible. Yes, I was here. Is it okay for you? Not yet? Question for the choice. At least 4% of peak computational performance report results everyone should expect. You should expect that if you have architecture compared to this one, so as well, this kind of stuff. If you have other architecture, more recent, more bit older, could vary a bit. So that's for my laptop. That's also for Must. It's 4%. With this version of Macro, if you get another version of Macro, it could change. But normally, would be rather this one. You should not expect 99% of peak computational performance here. It would be quite low, in fact. Yeah. maybe since we have a bit of time. So I'm pretty sure people are using this this image. So if I get U and I go, I don't know where. Of course. Okay, let's assume it's okay. So if I do, I don't know, if I get, okay, nothing here. I get this one, run IT stuff. Okay, I jump here on my laptop. So I get exactly the same lecture, of course. Here. I will do the same with a Podman inside my my laptop. So if you are a bit confused, normally should be quite straightforward to follow. And then I can pick this one. I'm not do everything again, of course. Or maybe okay, should be nice. And I get my report back, and I should be 4% again here, of course. That's the same binary, that's the same macro, so it's the same result. Same example gave me 64%. Yeah, some are already in the second example, so yeah, I have to move on a bit. So yeah, so here I use a second example. So I asked Macao to analyze a binary which is supposed to be auto-vectorized by the compiler, and Macao gave me 6%. I already. That's horrible. Okay, Macao gives me 6%. But here you have to be focused, because Macao gives is telling me that the loop is a pill-tail or unroll version loop. So it's not the main loop. That's the first one because it's a pill. But I don't care of this one. So if you want to have good performances and you see 6%, you say, oh no, it's just a pill. So nothing problematic here. So we can collapse this one, and here you get the real loop after that, because of course the compiler can do pill and tail automatically. So that's why I represent pill and tail in this path. In this lecture, and here I get 50%. So you can, pretty sure someone in the chat has 64. Could happen also depending on the architecture, on the compiler. Compiler could be smarter on other architecture. For my architecture, it's 50%. Could be better, could be a bit worse, depending of the binary, depending of the compiler, depending of your architecture. It's totally normal, but should be way better than before, because of course here I use vector register. I vectorize a lot. So the loop is highly vectorized, 97%, but there is some problem at some point. They should be fixed, but it's way better than before. Good point. But of course, if you get also the first one, you will have a hard attack, because of course 6% is a bit problematic. But that's a scalar pill-tail, so no problem. This one is really important, and normally should have the same here. So is it okay? Normally should be. Yeah, so they get the images. It's okay, nice. So you can get latest if you prefer. You don't want to be bothered with the digest, but I put the digest so you know the image is the right image. So here it's better. Yeah, 50% or 64 or whatever, but it's much better than before. So I have yeah, so that we have some time. So is it clear up to now? It's okay? Yeah, yeah, some question?
So when you actually mention peak performance, what is the peak performance actually measured?
Here it's a peak performance compute by Macao. So Macao will evaluate an ideal peak performance. So maybe I should show you in the report. You get don't remember, should be somewhere here, a bit after. Macao will assume to compute this peak performance. Macao will assume that all your data are fitting in the L1 cache. Because of course Macao analyzes the binary directly without any execution. So if you don't have the right data, Macao cannot do that. Sometimes it's a bit pessimistic about the speed up because Macao does not take account the pipelining as we saw before. So once Macao is telling you that you will have this X speed up, could be a bit better. And you have to be sure that all your data are fitting in L1 cache. Of course, if it's not the case, you will be memory bound, and that's not what you want.
Does it look at execution unit occupancy? Or
Yeah, also, yeah. We'll see that a bit later. Just the next example, we'll see that.
All right, thank you.
A question from Joseph. What was the issue with static library that you mentioned before? Macao cannot analyze static libraries, so cannot determine if the binary is well vectorized or not. You should use a dynamic library. That's a limitation of Macao. And another question from the Jeff, is there another tool that does take pipelining into account? I don't know if there is another one. Not in my knowledge, but maybe at some point, or maybe people working on Macao will do that another time. But of course, it's quite difficult because you don't get the detail of the pipelining because it's proprietary knowledge. So quite difficult to evaluate that. So okay, so Amin is happy. A question from Jacques. For backstage people, could we increase the sound of the question microphone? Yeah. Okay. Normally it should be okay. If you have another question, we can check if the fix is okay. Okay, so this is my laptop. This is must. And this is bare metal. No, this is bare metal here. Okay. In fact, I did it 3 times. Maybe I can do it one more with Obtainer. Maybe on Discord, do you want me to do the demonstration with Obtainer too? Because or you are not stuck anymore. Because I did with Podman, with Kubernetes, with bare metal. Question of Isabel. If I use Pixel, I have the error Macao CQA, alias CQA not found. Oh, yeah. I did that. I mentioned that at the very beginning of the presentation. That's strange because normally you shouldn't have this version, or maybe you pick the version. Okay. There is a good news about Macao. We have Macao on CondaForge. There is a bad news about Macao. We don't have CQA on CondaForge. So if you pick the Macao of CondaForge for now, CQA does not exist in the Macao binary, and that's a bit problematic. So that's strange because normally it's fixed. Supposed to be fixed, but I can fix it live because we have a bit of time here. So here in my Pixie, so I put Macao at some point. I did the test, and of course everything was failing because Macao has not the proper CQA value. So normally, if you command that and you redo Pixie lock and you drop your .pixie, or maybe I can show you. Maybe another one, yeah, or no. That's horrible. Okay. So if I say that, so let's pretend you get that, Isabel. You comment the Macao line 71. And so then here I get .pixie and a Pixie lock. So what I can do is I can remove the .pixie and the Pixie lock here right now. Okay. Question from Joseph. Does it mean in principle RISC-V pipelining would be easier to analyze? I'm not sure if there is a Macao for RISC-V. Normally, no. But maybe yes. We should ask Cedric and Emmanuel and all the team of Macao. But yeah. Where we can find the C++ file being compiled. Okay. You can question from Arslan. So yeah, you can find the. In fact, yeah, you can see that here. So in build 6 vectorization, efficient layout vectorization test. So maybe if I show you here, if I go in build, if I go in vectorization here, so in the build directory. And here you get all the different examples. So depending on which one you want to pick. So for example, efficient layout vectorization. Let's start this one. And here you get the binary here, O2, O3, and OFAST, because I compile everything with several times. So you can get the binary here if you want. And if you want to get that here, you can do the same. Build vectorization, efficient layout, or auto vectorization. That's the second example here, for example. And here you get the test auto vectorization. Give me some room, please. Here, O2, O3, OFAST. I don't remember. I get the O3 compute. So you get. So you can get also the simulation path here. So simulation. And here you get all the library, and they are even longer, of course, here. And here you get the Laplacian version, the auto-vectorization, the naive way also. So we start with the naive, we get to the auto-vectorization, and then we move on to the Laplacian stuff to see what's going on. So you can get all the binary here. So that's also another example before I show you an example with a binary, with a program. And here there is another example with a library. So you get the two examples. So normally should be quite nice. So it doesn't work on macOS, yes, because M2 normally should be deriving for ARM. So I'm not sure. You can try with Macao on ARM, on Arch64, but I'm not sure it's working. I don't have Mac, so I cannot check. But yeah, normally once you do some really computing, heavy computing, you are not supposed to use these. So Adrien said they have a special release for ARM. So here, see on their website. Okay. If they have a special release, normally you should pick it. Oh yeah, it normally should be a new stuff. Yeah, you should pick some other version if you want. So normally it's possible to do some magics. I never try it because I don't have Mac, but if you have a Mac, normally should be happy at some point. So Arslan said, I found the binary file, but I'm looking for the CPP. Ah, okay. You want the CPP. So if you want the CPP, you can ask Macao also, but that's the same. That's the same architecture. So if I go in, where are you? Simulation, and okay, very naive, you get everything, and then you get here the Grayscale layout. So here, as I said before, I challenged myself to have one main to do all the computing. So here, if I get this, come on, yeah. Here, so I define what is a Grayscale cell. So the worst possible layout, of course, because maybe I should not show you this because it's a bad example. We will see that auto vectorization, it was the second one. So let's try with this one. So here I use align vector Grayscale parameter. So I define my parameter way before. What I can show you here in parameter, for parameter. I said, okay, what are my parameters? So the same idea as clap in Rust. So you define a structure and then you parse it with some magics, and then you get all your argument of your program. So you don't have to be bothered with that. You have all the argument at one place and you don't have some problem. So of course, all the argument are the same for all the program. That's why we have a lot of stuff and some border and blocking stuff that we will see a bit after. This afternoon normally. And then here, so if I go back here, so you get the matrix, so to handle data, so with 8 matrix of U, matrix of V, so concentration of U, concentration of V, the output of U, output of V, because of course I cannot do in-out, I have to, because I have a stencil, so if I do an in-out, I will have a problem in terms of concurrency, so I don't want to do that. And I will have also some thread accessing the same data at some point. They will fight to get some result, and the result will be crap. So you don't want to do that. So that's really simple. And then the design is really simple. Grayscale mat. So I have to redefine the Grayscale matrix sometime. Grayscale initialization to put the first drop in the simulation, and the Grayscale compute. And of course, yeah, maybe I have to show you that, of course. Because I'm pretty sure we didn't, that's that bad. So if I do that, come on. Yeah, thank you. So I get here, and you should have this one, but that's for a bit later. And we'll use that also for the precision presentation. So, yeah, so you get the reaction spreading here. With these specific parameters from the simulation, because otherwise it's less funny. So of course it's important to do a thing right. So 1,000 images of simulation for the final final simulation. And normally was here, yeah. So yeah, this is a really simple API, of course. One structure and 2 functions, and that's it. But that's a simple starting point. Question from Luc. What did really make the difference here between, oh, come on, Discord, the two implementations, alignment, restrict, indexing? Ah, okay. So there are several differences. Yeah, it's a good question. So the first implementation is a bit too generic. That's in fact the very first implementation I did for the Grayscott school. If you look at the, I can do this here. So here, as I mentioned before, yeah, it's a really generic one. So I get our dynamic proverb is always broken on. It's so horrible to have VS Code, of course. Okay, so here, so I have. I compute something really in a really complex way just to see if the compiler can do something nice. Of course, it cannot. So the idea is to have the most flexible stencil as possible. So I compute the boundaries of the stencil on the fly, because of course, once you have a stencil 3x3, if you are on a border of your images, you don't have 3x3 anymore because you will be out of the image. So here I try to say, okay, let's pretend that I don't want to have extra allocation and just say, okay, I want my stencil to shrink automatically on the border of my images. Of course, the compiler is completely lost and cannot optimize it well. So here I do the first and last column of the stencil to see if I start with the first line or the second line or whatever. So that's really confusing for the compiler, even if I had to try, of course. So this is really complex. So of course the compiler is lost. So then that's for the data layout. So maybe I can use this one just not to be lost. So the very naive approach we did not get that is if you get a class with the cells and you try the object-oriented programming just to check if it's okay, but it's not if you are doing that too much. For the naive, normally you get something as before. Yeah, you get the max and min and you shrink your stencil. So of course the compiler is lost. Then we have the efficient layout for the auto vectorization here. Here, so I did what I thought before. I said, okay, no, come on. We need to have a 3x3 stencil. So let's tell the compiler, okay, I swear to you, it's a 3x3 stencil. So here I hard-coded the boundaries of the stencil. So K from 0 to 3 and L from 0 to 3. So it's not really elegant, but it's working. And then I don't have to unroll manually this stencil. The compiler does it for me, and that's really nice. And it's really also you see that it's really small compared to before. Come on, please. No, yes, maybe. Okay. So here it's really one screen function, really small. And if I pick the naive approach, you will see that it's way bigger here, because I have to compute the boundary of my loops, my inner loops here on the fly, and of course the compiler cannot help me so much. So here is way better, way cleaner, and of course the compiler will help me a lot with that. Can you question from Joseph? Can you pass a command for the simulation or the link to the web page that describe it? The command, yeah. If you want to play with it, of course, we are here to play with it a bit. So yeah, if you want, for example, to get this one with the auto vectorization, you get the command here to create. You can time also just to have a few here. So in full HD, so 1080 and 1920. With here, so 10 10 images and 30 steps per images. So the idea is the Grayscale reaction is really slow. So if you compute one image and then just after it a second image, you will not really see the difference. You have to iterate a lot to see the difference and see that everything is moving. So we speed up the reaction by 30 to have 30 extra steps between the two images that we get. And of course, normally it's written. So where are you here? Yes. If you want to, yeah, here if you want to have some picture, because of course here you will get an HDF5 file, and at some point maybe you want to get some picture because it's already nice to have some pictures, so you can do that. So create a PIX directory into your build directory, and then you can time also the creation of the images, and you will see that at some point, because I'm lazy and didn't optimize the creation of the images, so of course it will be slower than the simulation at some point if you have a really big simulation, but that's not the purpose of the lecture, come on. So okay. Yeah.
In the auto-vectorization example, in the .h file, I see that you use a vector of float with align allocator, whereas in the others, it's only a vector of float. What is the difference?
Attends, well. So you mean, maybe it will be better to show that to everyone. So you said it was auto-vectorization. So
yes,
this
in
one?
the .h file.
.h, yeah.
Yes, here, yes, you use a vector.
Yeah,
type.
yeah, that's a trick. I mentioned that really quickly. I don't remember which webinar, but never mind. Yeah, if you are used to use vectors, that's really nice. You do a lot of stuff with STD vectors, but they are not aligned by default. So what you can do, and that's an example I put here. So it will be in the vector. Should be somewhere here normally. Don't remember where, of course, but should be somewhere. So I show you here how to define a custom allocator. So the idea here is to say, okay, I want to use ST vector because I don't want to be bothered with pointer because come on, we are at 2026, so come on. But I want my vector to be aligned in memory. So by default, they are not aligned, but since people written the STD vector are really smart, they give us the opportunity to custom the allocator. And so you can write a custom allocator here. So for float, so you put the float twice, but that's the design of the custom allocator. And then you can say, okay, I want my vector to be aligned automatically on the right border. So it should be aligned on 64 bytes because I'm lazy here. Just a simple example. And if you do that, all the vector you will have will be aligned by default. So you don't need to have a pill. So the compiler does not know, so you will have a pill. But if you tell the compiler, as I mentioned a bit before in the lecture, maybe I can show you. It was where? It was somewhere. Oh, it was maybe the lecture of before. Is it the lecture of yesterday? Yeah, it's a lecture of yesterday, of course. Okay, so I will show you the lecture of yesterday. Where are you? Please come on. Okay, so yesterday it was, no, of course it's not the right, okay, this one, compilation, yeah. So here if I pick where is my Adama product. I always have an Adama product, of course. Okay, this one. No, not this one. No, it's not this one. It will be this one. Yes. No. Don't remember, of course. This one? Ah, this one. Okay. So basically here, once you use pointers, maybe this pointer is allocated by std vector, but you don't want to be bothered with new, with delete, stuff like this. So you put everything in a vector and you pass pointer because maybe someone else writes this kernel with pointers. And here you tell the compiler, okay, std assume a line, so I promise you that this pointer is a line on a border of 64 bytes. Of course, if you are lying to the compiler, as Vincent said, you will have a problem. But here, if I use std vector and I pass a pointer, but my std vector has a custom allocator and my allocator is aligning everything on 64-byte boundaries, it's okay. So you can do this kind of magic if you want. That's really nice because here you get the allocator. You don't need to be bothered with the allocation of stuff. It's done by the vector. You have the alignment because you use a custom allocator. And no, I'm pretty sure I don't remember if it's C++17 or C++20, you have a custom allocator inside the standard library, so you can use a custom allocator to align automatically, but you have to define it well. So here I rewrite one because it's nice also to know how to rewrite a custom allocator, could be nice. And of course, you see me come, if you have a custom allocator, you can align data, but you can use CUDA malloc instead of new if you want. So you can put some wizardry inside a vector if you want. It's totally possible. Okay, so maybe last example, and then we'll have maybe I can give you the last command, and then we will have the break. Or we do the break right now, and one last magic with Macao after the break, and then you will play with real computing and try to optimize stuff because that's the goal of the lecture, of course. So, okay, so 10:30, I think it's nice. So we'll have a break, 30-minute breaks. So you will go back at 11. So. Okay, so only we are back. And they are back again, so nice. Okay, so we'll do a last magic with Macao, and then we'll play a bit with the computing, of course, because that's the purpose of the lecture. So here we have 50% performance peak, or 64, depending on which hardware you have. And we can try a last one, this one here, to see what's going on. So always I will pick you the vectorized example. So the two commands here, so you can have a look what you want to do here. So with the Laplacian, so the idea is to split. Maybe I can show you also the code. Vectorization here, Laplacian. Where is my Laplacian here? So the idea here is to say, okay, I want to compute the Laplacian first for one species and for one other species, and then I combine the two to update the concentration. So here I have a bit more kernels, not only one big kernel, but several few simple kernels. So here I have the equivalent of before. So I compute the first Laplacian, then the second Laplacian, and then I update the concentration. So here it's in order. So here I compute my Laplacian with the loop that you already know, but I compute only the concentration for the Laplacian here. So I don't get the last part of the computing as before. And here I do only the computing to get the two Laplacians and the update of the concentration. So the idea here is to give to the compiler some functions which are simpler, so less computation, less branching, less stuff to do in it. So the compiler might be a bit better here to optimize everything. And of course here you have also possibility to reuse this function here twice for U and V. So that's the idea. So to split a bit, because of course if you have one kernel, sometimes the kernel could be a bit bigger and maybe the compiler will not understand everything you want. So it's important to simplify everything. So if you give me some room here, I'm on must, so I will do that at the same time here. Okay, so you can have the report here. And if I do the same with the HTML report, build, yes. Okay, and here I should have my report. Where am I? Oh, okay. Laplacian report, Laplacian, this one. Okay. So here is a trick. Well, oh, yeah, of course. Okay. So here the first path I get is the nice path, so 50%, and then I have the pill tail. So not the same order. So you have to be careful every time, of course, because sometimes you have it first, sometimes it's second, so you have to have a look. So, okay, 50%, we did the same, but we split everything. We don't get much, strange. Maybe we need more information here. We have 50%, but should be better. This is the time to introduce you the expert tab. So here, The loop is vectorized. We use 99% of the register length, which is better than before. Not much, but a bit. Here we get all the FMAs of the computing. So normally we should have some unrolling, this kind of stuff, because we don't have this much computing here. And if I go here in the expert tab, so normally at some point you should have the expert tab, you should use it, especially once you want to pick a reason why the expected usage is not as good as you expect. So here, if I get the vector efficiency ratio, so in terms of load, of store, of FMAs, of addition and subtraction, I get 100% roughly for each. I don't have multiplication because I have FMAs, so fuse, multiply, add instead. So cannot do much, in fact, here, because I have not much things to compute. So we get, for this architecture on my laptop, or for most 50%, for other should be also 64, stuff like this. But once you're kind of stuck in the performances, always check the vector efficiency ratio to see if you have a bit of margin, if you load too many data or store too many data, this kind of stuff. Here, 100% for everything we can do. We don't have division, we don't have square roots, so quite difficult to do much better stuff. And here, so this is the assembly. So that's a bit complex, but you get used to. So YMM, it's AVX register, ZMM is AVX 12, etc. And here you can see, okay, we have move, we have sub PS, and that's important to get this kind of stuff. So always, once you want to check the assembly, as Sébastien said also, you don't want to write assembly, but you need at some point to understand it at least a bit. So here, sub PS. So it's a subtraction, PS, packed single precision. So packed, so it's a vector. I call this this function on a vector. So I do subtraction of two vector registers and single precision, so float. So if it's a D, it's packet double precision. If it's S, could be instead of this P, it will be single simple precision or single double precision. And it's single, it's not vectorized, it's a scalar. And it's vectorized, it's P for packed. So you need to know the wording on this kind of stuff, but normally after that you can get this kind of stuff really nicely. So here I get the fuse, multiply, add. So for the Laplacian here, and normally should be quite okay. So you see you have a lot of information here for the latency, for the throughput. So it's evaluated by Macau. Yeah.
Do you know why it doesn't generate instructions with a memory operand? Like, so if we look at the first sub instruction, it doesn't operate directly from memory, which I mean, it would be.
You operate on the register here?
Yeah. So I don't know if it's AT&T's. Yeah, it is AT&T syntax, right? I mean, you would preferably operate with a memory operand, right? Or does it reuse the register? Like, does it reuse, for instance, I see that 0 is reused 2 lines below.
YMM0 is used here. Maybe with some coloring is better, but we don't have coloring here. So you have the 0 here, you have the 13 here, you have the 14. 14 is a result. So you add the 14, you reuse the 14 here. So that's you jungle with all the vector register because you don't have much. So you have to. That's the trick for the compiler. You can follow it. That's hard, but
Okay, but you think the code is quite optimal? Or I'm just confused why it's not generating arithmetic operations without memory operands. Because I mean the AVX instructions that allows for that, right?
In fact, yeah, there is a trick. Here you have you need to mix, once you sub PS, you subtract in a vectorized way, so 2 vector register, but you don't know the size of the vector register. And the size of the vector register is given by the name of the register. If it's a Y, you know it's AVX. If it's a Z, you know it's AVX512. So you have this this command to tell you what is the operation, and then you should see the naming of the register to see what is the size. And with the habit, you finish to manage that, but the first time it's quite confusing, of course. I agree with you.
Okay, thank you.
So if it's your first time writing assembly or reading assembly, if you are confused, it's normal. You need to see several times on maybe smaller kernels or this kind of stuff to be sure that everything is clear. Or maybe I can show you with a smaller kernel normally. Oh, this one is big also. Or I can, maybe the very first one was not too big because it's not really well optimized. This one should be simpler to read. Yeah, much more smaller because the compiler cannot do much and cannot unroll stuff. So here, so I do some initialization with XMM because it's not vectorized, so it's SSC4 here. And here you see it's add and not v-add PS. So here you have some packed computation with partial vectorization, so it's AVX here. And here an I add, so it should be the counter, I believe. And you see that it's really, really small. Normally I should get, yeah, I had this one here. So add SS, so add single simple precision, as I said before, maybe it's more clear now. And here you have the jump not equal, so if you get, oh, the condition is gone, okay. If the check you did before is false, normally you jump, and you jump with the right address. Where is the address? Ah, top, okay, so the address here, the top of the instruction is this address, so I move on here and I do everything again. But say maybe it's a bit too much for you have to get used to it, but it's important once you don't get the gain that you are expecting. Of course, it's not the one I expect because it's not the proper tab. This one 50%, but it was 50% before. Even if it's a bit better, why is the problem? And then you get the expert. And vectorization ratio, it's really important to have in mind. So you can get most of the information here, but if somewhere you say, oh, I don't understand, I should have an FMA here, but I don't have it, so I don't understand why, you can search for the FMA here and say, okay, here I have an FMA, it's okay. Here I have an FMA, but why? I don't know. Here I don't have an FMA because maybe it was a problem of parentheses, of stuff like this. So here's really for checking, but normally for most of your kernel should be quite. Okay. That's strange. I have 100. So question from Lutke. That's strange. I have 100% Pixie G++ 15 Ryzen Gen for Ryzen. I don't know the Ryzen by heart, so Joseph got 75% of Ryzen Gen 4 with the same compiler, or with not, or maybe you have subtilities. The 2240 address is an address inside the program. So in the memory, once you jump in your program, once you have a call, because of course a loop does not exist, so you check if the condition is true. If the condition is true, you jump, or not equal, here the jump not equal, you jump to the address if it's true or not. Okay, so normally we can move on. So now we'll play a bit. And so here the idea for you to play with is I give you a script. So with a script evaluate perf simu matrix, so I can show you here. So if I go, please, if I go into 10 and I get this one, so it's a small script. No, you don't want. Thank you. So just a script, you pass all the rows on the columns. So here, the first argument in double quote and second argument in double quote. And the goal is to find the best shape possible for your laptop, on your laptop, to get the best performances. So once you remember, once you compute, you do a performance test, you have the full time of your computing and the time per element. And the game here is to find, for your particular architecture, the best computing in time per element. So to see in which size of the image you get the best performances here. So not the total time, because of course if you have less element, you have a total time which is smaller, but the best shape that you can have with the best size per element. And normally I already put that in the README here, but I will give you we are not up to date. Okay, so I will get here. Yeah, here. So we can start gently with this one, for example. So here you have to play a bit. So I will do that at the same time of you, of course, because it's fun to play with that. So typically this kind of stuff. So assuming you are in the build directory, so you compile everything as before, and you can just play with a few sizes here. And I let you 10-15 minutes to play with everything and see what you can do. So I can do the same, maybe will be yeah, here for example should be quite okay. So it's a wide range of possibilities. So of course after that you have to play with it and to change the sizes to see what's going on and to try to find the best size possible. But they have to play with everything to see what's going on. So maybe the size of what Joseph is asking. Yeah, the idea of this is you have a program. So here the simulation, the auto vectorization program. So we just check with Macao, and the idea is to find when you ask the program to compute a certain image size, the image size where you have the best time per element. So you want to compute here, and you want to have the slowest, the smallest time per element possible. So not the total time, but the time per element, as we explained yesterday, and I has explained also a bit this morning. You don't have the user bin time. Why user bin time? It should be time normally. Or maybe you are saying to me that where are you? Here? No, I have too much tab open. Here. Ah, yeah, okay. Normally you should have user bin time. If you don't have user bin time, what you can ask, or maybe I can do it here also, so you can see. Some weird stuff normally. No, of course it would be too easy. So if I get this one, okay, and I get the fix is coming. If I do that, I get bin and I get time. I should have, yeah. Of course, Pixie is tricking us. So if you do that, really annoying to have this big of a screen here. Please, thank you. Here, of course. This, and this should work. And maybe what I can do also, so here normally I can prove it to you. If I do that, it should depend on the image you are using, because some of them have time and some of them maybe don't have, or maybe you pull them too early, it's also possible. But normally it should be okay. And if I get, where are you here? Normally it should be okay. Yeah. So I can give you this. No, please. Okay. So, time. Okay. If you are on bare metal and you have tab, it should be okay. If you are on a Pixie environment, if you use this command, it should be okay also. Okay, so this is done. So maybe I can show you the result here. So you get this kind of result. So here it's should be the total time here, elapsed time in second. And here I have the elapsed time per element. That's the thing we want to optimize. And here you see, here, of course, it's really small matrix. So I don't vectorize, I don't take advantages of the vectorization. And here it's a bit too much. So I have too much memory to deal with. And I'm out of the N1 cache. So you should see around here what's going on. So 3 nanosecond per element. So please get out of here. Thank you. So here, 3 nanosecond per element here. So explore, on my laptop at least, explore around 128, so maybe 64, 226 to see what you want to do. And explore also with non-symmetrical images, because here it's a square, 32, 128, and 24. And the same for the width. But of course, sometimes we'll have different performances. If we change the size, if you have vertical images or horizontal images, so you can check also that. And by doing few tests, normally you should get really quickly to the best one. So maybe I can do that also live. So let's pretend that, okay, I want to have 32, so yeah, 64 maybe 64, and maybe 256, and maybe here, yeah, 1024 is a bit too much, maybe 32, maybe 64, and maybe something asymmetric at some point. So 56. And maybe here I can add 26, this kind of stuff, just to see what's going on. Less green is better, yeah, because red in in Numpy is really horrible. So yeah, whiter, if you get something whiter, yeah. That's the best color map I found in Gluplot to give you this kind of stuff. So yeah, Joseph, less green is better. Otherwise, it's quite difficult. Also, if you get too much green, get hide. Oh, so you just finished. So yeah, of course, here you see that I zoom a bit in what's possible to do, and it's much faster because, of course, I'm starting to get something really efficient. And even if I have more tests to do, they are really faster, so I can get more quicker to something really nice. So here, if I continue, I get 3, 2.8 here, quite nice. So here I start to have less asymmetry, less symmetry. So here 331, if I get something really symmetric, and 2.8, 324. So here it's something interesting. I can go down a bit and explore around here, and you can do the same. For your laptop, of course, don't get everything the same, because if you don't have the same architecture, so of course, don't want to do it. Okay. We had a question from Stevenson. We had to make a choice by the end of this output. Yes. Once you have the output, so this output, you say, okay, now where is the best output? So here I get 2.8, but here I do 2.67. So 3.62. So maybe this one is better. So a longer image, more columns and less row is better, but quite a nice amount of columns. So here you see it's quite better here, but it's even better here. So yeah, and then you can explore around this part and get get to the best performance. Stevenson, question also for Stevenson, is there any text output I interpret instead of the heat map? No, because I didn't thought about that. So I prefer to have a nice image, so it's okay. Or maybe, yeah, this kind of stuff. So the question for width and S correspond to a number of pixels, yes. So you have the width and the height you pass with all the combination you pass with all the number of rows and number of columns you pass to the script. So yeah, I don't understand what we are calculating exactly. Can you explain the question we are trying to answer again? Okay, so here you get the elapsed time. So it's not what you want to see. So the question is here. You have three, but let's pick two. For now, you have two outputs. You have this one, which is the output with the total elapsed time of the computing. So of course, the bigger the image is, the longer it takes to compute. That's normal. But what I want you to optimize is the size of the images to get a better time versus the number of elements you compute. So the ratio between the total time and the number of elements you are computing, so in nanosecond per element here in this case. So the second, maybe if I do that, you get the name. So here's the autovec, so this is the name of the program. So NSL, so nanosecond per element here. And so if you pick this output, so you should get here the output. Of course, if you get a bigger image, you have a bigger, normally bigger computing times. Here it's a bit different because the images are really, really small, so the IOs are dominating a lot the computing, so you get better and then you get worse. But this is the one you want to do. So the number of nanoseconds you need to compute one element. Because if you do that, you can tell me, okay, if I have this size of images, I have the best performances, I have the optimal performances on this architecture. And of course, we will use that for the blocking this afternoon. So it's important for you to understand that. So here, basically, I show you how to find the optimal size of block you will use for this afternoon. So it's important to search this. Of course, you cannot write documentation and say, okay, this one. So Michael has a question. Text output will be nice to analyze usage in script. Yeah, or at least you can add an echo for the time and say, okay, I have this time per element, and it's okay. So Joseph is happy. What are elements in this case? Yeah, you should. Yeah, it's a really good question. You should be a bit careful because, of course, nobody agreed on what is an element. So here, for me, one element is a computed element. So one output. So of course, we read 9 cells to produce one. So for me, it's one computation, one output. Because otherwise, could be a bit trickier to do. So my definition here for this lecture, for this morning, in fact for the week, is one element is one output. So one new cell in the output, one pixel. What we are doing to the images. What images? Question from Jacques. What is it better here to have more columns instead of rows? Ah, that's a good question also. Okay, it's working. The plan is working. So what is it better to have more rows or more columns in that case and not more rows? Do you have an idea of that? Compared to what we all explained yesterday and this morning? Yeah.
So, correct me if I'm wrong, obviously. It feels like rows are the contiguous memory part, and there's a limited amount of things we can vectorize. So we should have a limited number of, a very precise number of elements in the row. And then if we go over that, it won't fit in one vector. And I'm not sure if that's
It's that,
related.
exactly that, yeah. We choose here in the implementation, if I show you again, where am I here, for example? When I walk to my vector here, so Matthew, let's take Matthew or Matvit the same. So here I have one big array at the, because it's always faster to do that. But I treat this array as a multidimensional array by the indexing. And here I have Y working on the eighths of the image, so the number of rows of the matrix. And here I have J working on the width, so number of columns of the matrix. And I compute this way, so I times width. So here I pick the right row I want to use, and then plus J to get the row and the pixel I want to use. So of course, here I loop over J. So here I loop over contiguous element in memory. If you are doing the same stuff on Fortran kernel, for example, the convention in Fortran is to have the first axis contiguous, the row, so row axis contiguous. And of course, here you will have the other answer, because here in Fortran, we do more stuff in rows contiguous, and in C++ it's column contiguous. So row-wise, column-wise. So we have one column per column in Fortran, and we have one row per row in C++. So that's why there is an asymmetry, because of course, if you say, okay, I go down, but I read my data like this, I will pick my sector like this, but I will read my data like this. So I pick one sector for nothing each time. It costs a lot, of course. If I do that, I write all my elements contiguous to each other, and of course they are already in the memory because I read the cache line, an entire cache line, so it's much faster. That's why there is an asymmetry, because of course the memory inside the hardware is not symmetric here. So you get the asymmetry here. Really nice question, Jack. Okay, Lucas, it should be a multiple of 32. Yes, in my case, because I'm on AVX, AVX2. So it's better to have a multiple of 32 because you don't have any peel or tail. And why for GPU, I see warp size, but for CPU, it's linked to be register. Yeah, but vector register have a size too. So you need to take account, as I explained before, with the peel tail stuff. If you don't have a multiple of pixel, which is a multiple of a vector, the size of a vector register, you will need some peel, some tail, some zero, some padding, some stuff. Otherwise, you will lose and finish the computing element per element. It costs a lot, in fact, in terms of computing. So yeah, that's why also if you are using BLAS libraries like Atlas, like LAPP, stuff like this, once you do some performance tests with discrete but one per one size of matrices, you will see annotation like this in the performance because you pay a lot because you don't have peel, and then you don't need peel again, so you have a better performances because you vectorize really quicker, and then it's degrading again, and that's why you have this kind of shape in the performance. Question from Stevenson, is it related how the vector have processed row measure? Yeah, it's exactly that. Row measure, column measure. So here it's a row measure because it's C++, so follow the C++ convention. But of course, if you do the same with the Fortran example, you will get another stuff because of course the data are not aligned the same way. Okay, Jacques is happy. It's nice. Oh yeah, that's really important. So to show you really with the performance test, it's not symmetric, it's totally normal. So you cannot say, okay, can do whatever I want. No, the hardware will get you will get different performances depending on the convention and on the hardware. Because normally she's happy. So here I try to do a really big test, of course, before, because it's really long to compute. So don't do that right now because it takes a while. But here you can see if I do this heat map with a lot of different value, you will see, okay, here it's quite interesting. And you start to see that it's asymmetric, of course, because here it's 7.82 and here it's 5 or 4 here. So you get the asymmetry here already. And here, of course, I'm supposed to zoom a bit to see what's going on. So here I get, as I explained, here my image is really, really tall, and here my image is really long. So of course, since it's C++ row-wise, this is much more efficient compared to the convention I follow. Of course, you can use another convention if you prefer. It's up to you, but you have to be aware of that. And that's okay. And maybe can show you a final trick if you don't have more question. But if you do, it's okay. We can continue to ask question, to answer question, no problem. But we have a quarter of hour, so I can show you a last thing. It's the same idea as this one, but with another tool. So an embedded tool, if you prefer. And then we will be on time to go to lunch. Okay, Joseph is asking, can you pass the command for generating that new image? You want the full. It's really long. It's really long. I am pretty sure I have it somewhere. I have to. Where is? No, not you. You, I think. Okay, this is the command. So that's really long. You should be patient if you use that. But if you want to get exactly the same output as me, with different values, of course, but with the same shape, it's this one. So it's really long. So don't do that right now if you want to do the next trick. So here, in fact, it was nice to have a little bug. So now you are always aware that we time everything with time. So the time program, not the time command of bash. So we get the full computing time, including the allocation, including the saving, including everything. Of course, if you want to time computing, maybe you don't care about the allocation, you don't care about the saving of the PNG files or saving of the HDF5, you just care about the computing. So using time here in a high-level way, it's not really what you want to do. And so what we can do for the last stuff here is to do the same, but with another script here. And I will show you, of course, what the script is doing. And I'm pretty sure at some point I will have to do this trick also inside it. So of course, remember, in fact, no, because there is no time, so normally it's okay. The script make a simu matrix here. So give me some room, please. Come on. It's horrible. Okay. So here, it's a different approach. Before, the performance computing was done by an extra tools, so time in that case. But here, since I have one main, I can do whatever I want with it. And here I can ask directly with extra parameters the program here. So the program I pass here in the parameter here, because of course you can pass the program you want. I can say, okay, the program, I put the height, the width, the number of image, the number of extra steps, and I can ask the program to say, okay, I want you to measure your performance yourself with the probe I showed you before, with the little timers I showed before, and I want you to output the performance in a TOML file here, this TOML here, and then you get the performance per element, the number of nanoseconds per element, the number of cycle per element also, because it's important to have both, because sometimes the hardware is tricking you. And by doing that, here I make some plots at the end. Maybe I can show you also the results if I put this one here. So here we care about the computing time only. So we don't care about the time to allocate, the time to save the HDF5, this kind of stuff, only the computing time. Because of course you can be biased, especially if you have really, really small images, because the allocation costs a lot compared to the computing, and maybe not want to be biased for this one. No, you. Question from Stevenson. Do you recommend hyperfine in this context rather than time? I never use hyperfine. In fact, I like time to get some even the page fault sometimes. Maybe hyperfine is better, but for really thin measurement, I prefer to do it inside the binary itself, inside the program itself, to be sure that everything is nicely done. And I measure what I want to measure. I don't measure the whole program, but only the part I want. So it's a bit long, but it will be. Maybe I should try to zoom at the first place, because of course you already know this. So instrumentation, yeah, Stevenson. To be precise here, I prefer to do this. I log the computing with a timer, and then I'm sure that I'm measuring what I think I'm measuring. So question from Luke, hyperfine is the statistic which time doesn't. Yeah, times, that's a bit of problem with time. You do it once and then you can have a lot of bias also with time. So here, I'll trick you a bit, of course. The computing time was nice with time, so not too long, not too small, so normally it's quite okay. Of course, it's really, really small. You will have a bias with time, and it's better to use other thing. So yeah, you have always to criticize the method you use to get some performance evaluation, because of course it's not always the same. And, a question from Joseph. Would hyperfine be good for benchmarking physics, chemistry, simulation program? I think it depends on the program. If the program is really long, maybe you have too much stuff in it. If you just want to time it and to see the total time, should be fine. If you really want to focus on the computing time, maybe you will have a lot of data movement and stuff like this, or saving on or system call that you don't want. So you always have to. So it's up to you, depending on what you want to do. So where are you? Almost. Okay. Yeah, we're on time. It's nice. You have any question in the audience? It clear? Yeah.
Yeah, just basic questions, but I don't really understand what's the difference between the files name. The file names aren't very clear to me. What is NSL log? In the
The
output?
NS, it's nanosecond per element. Here.
Oh, so it's different.
You get here
units?
in the, come on, please. Yeah. Here, elapsed time per element. Just to.
Oh, in logarithmic scale.
You get the NSL. So here
Okay.
it's elapsed time per element. So I divide the total time per the number of elements I compute. And here, with perf matrix here, I have the elapsed time in second for the total computing, but just without the normalizing it with the total number of elements computed.
Yes. Oh, thank you. Also, I'm struggling to have an intuition to, when you showed, I think, a result with green on the outside, on the rim of the graph. What was that for? Because it seems like sometimes it's more like a gradient towards the bottom left or the top right.
For this one, yeah.
Yeah, that one, for example.
Yeah, here I have vertical images. So I read rows per row, but I don't use my cache line efficiently because I just drop down and everything I get is wasted because I want to get the one just under the hood. So of course, nothing is totally wasted because there is no cache trashing here because I have only four tables here. But I read a lot of, I put a lot of data in the register or in the L1 cache, but I read only one element, and then I put the next row in the L1 cache. I read only one element out of 4 or a bit more, 8 in that case. And of course, it's a big waste of time because I have a lot of bandwidth that I don't use for computing. I just put data in my cache, but I don't use them. So here, since we are reading the data in row-wise, of course, if you read column per inside the column, you will waste a lot of time because, of course, all the data you are using are not, you are putting in the cache are not used, only one. That's really bad. Here, you get much better performances because, of course, it's not really efficient because you don't take advantages of all the cache or the vectorization, but you read the data in the right order. So if you put data in the cache, you read all elements you put in the cache, and then you read the next one. So that's the main difference here.
All right, and the part in the center, it depends on the CPU model?
Yeah.
So what we should read there is the size of the cache lines or the size of what's?
Yeah, here you have the size of the cache line. I will explain that in detail this afternoon, but
Okay,
basically you have the size of the image. You want to be sure that here the full image is in the cache because it's one block. So for blocking, of course, the block should be entirely in the cache. But the point also here, you have some subtleties because, of course, you read 3 lines at a time because you have a stencil 3 by 3. So the line before, the current line, and the line after. And you have to fetch all this data together to be sure that you can compute your stencil. And of course, the problem is once you are at the end of the row of the image you want to compute or the block you want to compute, if you take the next row and you have a block so long that all the data before are gone because you have a too small cache, you have to refetch again this data. And if you have less column, you can say, hey, I'm at the end of my row. I get the row, the next row, but the row before is already in the cache, and I don't have to throw it away. So I will expect that with a nice illustration this afternoon. It will be more clear. And maybe, okay, you are done. So maybe I can show you also. So here I have a bunch more if you want to play with that another day. So I have the cycle per element here. So I do the benchmarking here automatically with several probes. So I get the RDTSC, so read the timestamp counter, so a probe inside the hardware, and a nanosecond, so chrono. So here I get the cycle per element. So here I would say, okay, 254, 246, it's quite nice. So let's pick this one. And if I go with, okay, cycle per element here, I get the log version and the not log version. In nanosecond per element, here I get 594. Sometimes, that's also important to have in mind, but here I'm lucky, but that's unfortunate for me because it's nice to show you if it's not working. But sometimes in fact, I can show you maybe this way if BTOP is happy. Yeah, here I have 800 megahertz. Of course, my CPU is doing nothing because I'm just presenting some stuff. I'm not starting computing stuff. So everything is variating. So if you ask the CPU to check the number of nanoseconds you put per element to do a computing, if the frequency of your hardware is changing, of course, the result is a bit biased. So here normally the maximum is 4.4, and here I am at 0.8 gigahertz. So of course, if you have both the nanosecond, the time in nanosecond, and the time in cycles, you will see that sometimes they disagree because the frequency was changed during your benchmark. So that's also important to have in mind. Sometimes your timer is a bit biased, and so having two not related, it's nice to see if you get unlucky or not. I'm pretty sure now we can stop, except if there is a last question. Joseph has a question. I'm curious why 40 by 40 would take less time than 32 by 32, because it's the total elapsed time. 40 by 40, you are here. 32 by 32, you are here. No, 32 is here, and 32 is here, so 0.45 and 40.03. Maybe here you did something. As I explained before, it could be a problem of chrono, but I'm not sure if you which script you use for that. Yeah, that's why good point, Leon. That's why also one stuff that you can have, if you have really too small computing to do, there is a warm-up. So as I explained before, my computer is resting and having a really slow clock because it does nothing. And then when you start, the CPU has the time to realize that, okay, you want to compute, and then the clock will increase a bit in frequency. And during this type, of course, the performance are really bad. So that's a warm-up. We'll see that a bit later, but yeah, that's important. So questions from Luke. Harold looked pretty too. So yeah, you get 0.05, 32, and 0.1 for 64. Yeah, you get the full time here. You don't get the time per element, so of course it's increasing. So yeah, that's pretty normal. There's a last question in the audience, so it's okay. You want to lunch? You're right. Yeah, I think we can close. Otherwise, people from the restaurant will yell at us, so it's better to stop. Okay, so we'll stop here for this morning. So thank you everyone for following this this lecture this morning. So we'll start again at 1:30. So for the presentation of the GCS satellite sat, so the Germany satellite sat. So thank you again for everyone. Thanks for all the satellite sat for following us, and thank you for all the questions, all the comment. It was really nice. We start again at 1:30, and we will start again the lecture at 2 p.m.
And we are online. We are live streaming. Floor is yours.
Hi again, everybody. Welcome. I am Mary, the organizing team on the Graceful School. And now we move to the satellite site presentation slot. It's an opportunity to highlight the international dimension of the Graceful School and the community participating remotely from around the world. So this is the first of our satellite site presentation. Throughout the week, we'll hear from many sites joining Graceful School 2026 across France, Luxembourg, Netherlands, Croatia, Slovenia, and Senegal. So today we are pleased to welcome CC-FR, representing our partner site from the German Specialist Center, who will introduce the German satellite site and share a few words about their local community. If you have any questions, you can ask them later or even on Discord on the dedicated channel. So please enjoy.
Yeah. First thing, what is our competence center? So we are actually a combination of 3 HPC centers, which are also aligned in a crowd of certain centers for computing, which is the High-Performance Computing Center in Stuttgart, where I am located right now, and the Supercomputing Center, the Leibniz Supercomputing Center in Munich. And we also have a partner which is taking care of complex industry, which is CUDA. That was are the partners of our National Competence Center. And our task is providing user support for the users of the supercomputers, giving training, education, supporting industry, since we are also connected to industry to some degree. But we are also cooperating with other international and national partners. Some of them you can see here on the slides. Smaller centers in Germany, for instance. And we are, of course, also operating the systems and providing access for research. Until now, what you have seen in the presentation so far are usually only how you are using one node, so optimizing one node, which is called a subsystem, but of course an entire PC system is mostly a cluster of such nodes connected via a fast network. And that the process computing is the biggest research. Systems we are currently operating and in traditional CPU cluster would be the cluster, which is nowadays rather slow. Here we have 10 petaflops per second performance. That was just on the picture before. But we're also operating currently the biggest system in Europe, which is called CUDA. That's a combination of the NVIDIA Grace-Hopper superchip. We have each node 4 times 72 cores CPUs and 4 times 132 core GPUs or multiprocessor GPUs and about 5,900 of such compute nodes are combined in one big cluster. The performance is a bit more than 1x. That's right now the current biggest we have in Europe, and that is one of the centers which is connected in Annecy. However, as I said, we are also offering training, and as you can see, we are trying our best to offer a lot of training courses. So in the last few years, we most of the time offered more than 100 training courses per year, which lasted over 280 days around about per year, and had several thousand participants per year. However, those are not unique participants. That's just the rough number of all participants in all courses. Topics we are offering courses on is more or less everything related to supercomputing AI stuff, meaning quantum computing, parallel computing, performance optimization, tools, programming languages, GPU programming. But that one, the deep learning, machine learning, is currently outside of the national competence centers, but all of our centers are also connected to AI factories. And in this frame, we are also offering deep learning and machine learning courses, and many more. And if you're interested in our training, it's just supercomputing in DE/training. We are, as I said, also offering support for industry, for instance, but also for academic users. One example here now on the slide, there's an example where there was done a simulation, finite element simulation of a welding process, and that was done with a commercial company. And point was that if you are simulating this, the impurities and the like in a welding process, then that takes only a few hours instead of 4 to 5 expensive examinations per year, and costs are much lower for that. That is one example where we have been working with industry. And but of course, our main focus is actually academic research, public research. So one example you see here on the slide is there's a more realistic simulation of an interstellar medium in the context of galaxy and star formation, which has been done by a multinational research team. And you can see numerical analysis of the solution of a bilateral hydrodynamic problem. And that was calculated on a CPU cluster, in this case, at our partner LSZ in Munich. And yeah, they used a lot of compute time, but also a lot of memory. That was some examples what have been done. And as a National Competence Center, we are offering the full pipeline from the initial context, if you're interested, if you want to do something with HPC, to how you get access, how you log into the system, how you apply for a project running on such a system. And afterwards, we will help you how to use the system, how to do data management on the system, how the software environment looks like, what is available, how it works, and finally, how to do the post-processing of your results, how to visualize them, and the like. And that is what our National Competence Center is more or less doing. And if I have sparked your interest, or we have sparked your interest, and you would like to learn more about us, then please just contact us. You can directly reach me here in Discord, or drop me an email, or just write us, or just visit our website. And I said that we are also connected to an AI factory. So since now AI is no more included in the portfolio of the National Competence Center, I want to show you our AI factory where we are as HLRS are part of, and that is called Hammerheim, which is a hammerhead shark, more or less, in German word. And key features and goals are we will provide soon a dedicated AI optimized supercomputer for that at our compute facility. And the AI factory tries to provide a seamless transition from a laptop to the or cloud to the AI supercomputer we will offer. And of course, all the services around, meaning we want to try to link you with European and international AI initiatives, or give you access, or at least connect you to the ecosystem in Germany. And of course, also technical consulting, customer training, and onboarding support will be provided by the AI Factory if you are in the AI field. And just to give an outlook to the system that should be delivered in the next few months, will be an NVIDIA system in this case with 215 GB 200 NVL4 nodes, so 860 GPUs in total. A few other nodes from a company from the Netherlands, and performance would be around 15 exaflops peak in AI interference performance. So that's of course not double precision in that case. Yeah, and I think I was too fast, but that leaves us for more time for exercises. So get started, meaning if you are interested in connecting with us, having a job you want to run in AI, then you are welcome to reach out to us. So companies, startups, researchers, a particular focus of the Hammer High AI Factory is really companies and startups. So if you're planning something in that direction, just reach out to us and we'll see how we can get you onboarded. And that's it. Thank you. And so I still have a lot of time for questions. Are there questions?
Yeah, thank you, Tobias. That was great, really insightful. So you have question in Annecy, you can take the mic. If you have question on Discord, you can write them down.
Yep, let me open Discord. Questions just where will I have the questions in Discord? Oh. So please let me know if you have some. If not, then I assume you're completely satisfied.
We have a
Someone
question.
is typing something. Okay.
I have a question. You said that you have some tasks related to quantum computing on your systems. So I wanted to know how your supercomputers are used for quantum computing tasks.
On Discord, I suggest to use the dedicated channel, the German site can help. Or in Annecy, do you have questions for Tobias?
Sorry, so I'm going to repeat my question. What I was saying is that you said that you have some tasks related to quantum computing. So I wanted to know how your supercomputers are used for quantum computing related tasks.
Well, that depends a bit on what you actually want to do. So, of course, you can use a supercomputer to simulate a quantum computer, but that's probably not what you have in mind. There are two systems, one in Munich, one in Jülich. Jülich is in quantum annealer. In Munich, that is a more traditional quantum circuit-based system. Connecting them with a supercomputer is still sort of an issue. You could, of course, use both of them. Problem bit is scheduling on both systems at the same time. But one application that has been explored is that since you are still in the NISQ era, where you have the issue with all the noise in a quantum computer, to try to use algorithms such as what was it called? QAOA, where you try to evaluate results on a quantum computer and improve it with a classical algorithm, state information on a classical system. That is one thing that has been explored. That would be one option, how to combine them. We will see what will be available in future once the quantum computer gets more stable. I hope that answers your question. If not, please let me know.
Yeah. Thank you.
Other questions? I will check Slack. Not Slack, sorry. Discord. But I don't see any questions in Discord right now.
I think we are good on our side. I just want to say thank you again and a round of applause.
Okay,
Yes,
thanks.
thank you, Tobias.
Thanks for the opportunity to present our National Competence Center here.
Well, feel free to reach out to Tobias on the dedicated Discord channel, the German site. If you have questions later, he'll be available. And I will resume the course at 2 p.m. So in the meantime, don't forget to grab some coffee so we all stay as responsive as our servers this week. Okay, see you later.
Okay, so welcome back everybody. So we'll continue a bit of black magic with blocking and advanced blocking as we started this morning. So this morning we try to get the best size of the images possible, to get the best performances possible. And of course, this will be a brick for the blocking for this afternoon. So the idea of blocking is really simple. You have a stencil, so 3 by 3 in this case for the lecture. And once you compute a row, of course, you have a stencil around the row. So you need to read three rows to compute one. So a cache is 48K on my laptop, 32K on most computers, as Sebastian mentioned yesterday. And of course, we have 4 tables here, tables of floats, so 4 bytes for each. So then we need to put 3,000 floats per block, otherwise we will go out of the cache, of the L1 cache. So 1,000 floats per block for 1 row, and we have 3 rows, and we are just in the cache with 1 row only. So the images are longer in Full HD, so 1920, 1080. So if I do that with 1 row only, for the first row, I get everything, okay, but for the second row, just after that, I have to reload the first part of the row before to be able to compute the rest. And of course, that's a pity because I managed to go down in the cache twice, which is a bit too much. So what we can do is to change the shape of the block, and we say, okay, we want to reuse as much as possible the L1 cache. So we put 1 row in the cache, but for the next row for computing, we want to keep it, to be sure that we just have to read 1 more row and not the row before. So if we have something in a more square shape, well, it's quite okay here. 3,000 values per block, so 100 rows and 30 columns, 30 rows and 100 columns. So I can reuse much more. Every time I finish to compute a row, I can get the next row, and all the previous rows are in the memory. So that's why also this morning was faster in some shapes and not other shapes. That's the reason. So the previous row is always in the L1 cache. It's okay. And we have an overlap, so we're happy because we go down in the cache only once. That's a good point. So if I don't have block, I need 3 reads from the L2 to go down because the L2 is bigger, to 256K or a bit more, 1 megabyte some cases, but normally it's okay. Here, I want to be in the L1 cache as much as possible. So of course, if I have block, I have 1 read for the L2, but 2 from the L1 because I already have the information available, which is good. So to implement that, so it was a design of Sébastien, of course, because we did that together. And so the idea is to have an axis, so just to manage indexes, right? Only the indexes, so you can see that as a view range, if you're familiar with C++23, so the same ID. And a block is 2 axes, 1 for the row, 1 for the column, 1 for the width, and 1 for the height, if you want. And we can do the same, and we express the blocking just with the index, which is much simpler, and Sebastian will do a demonstration also for that a bit later. So we did this kind of stuff this morning to find the best block possible and to have the most efficient block here. So we explore a bit. It was a bit tedious, but you have to do that at some point to be sure that everything will be okay. And we can start to do something much powerful, because here I reuse my data on the row, on the first row and the row after. It's nice. It's really nice. But as Sebastian said also yesterday, diving into the L1 cache costs a lot, and doing it only once, it's better than doing it several times, but once you get your data in your L1 cache, you want to reuse them at some point. But the problem is you don't get the information. So what if I put my data in my L1 cache with a block, but I reuse the block as much as possible, and then I do other things to use a lot of time the same data I just put in my L1 cache. So at each iteration, we spread the information from 1 pixel. So we have extra steps. So if I have a block, let's say 8 cells here, I can say, okay, for the second time, I cannot compute the new values of the extremity because I don't know what's come after that. But inside I can, because the information, I have all the information for that. And I can continue to do this in the future. So we build a kind of pyramid in the time here. The good news is we don't need the inner values. Otherwise, we will consume more memory for the computing. So we have to take care about it in a cache. But the good point is you can do that. And so we have the middle of the block, which is as long in the future as possible. And the extremity, we will have to figure out how to get them in the future at some point, but that's another problem. So that's really nice because we need the same amount of memory as before. Just the algorithm is different. So if I have 8 cells, I have something like this. We need to go in the future at some point, and then we need to complete the pyramid at some point. So how to do that? So if I iterate with 1D, with my block, I can say, okay, classically, what we did this morning was, okay, I want from image 1 to image 2, and I have a bunch of extra steps. As I said this morning, this reaction is really, really slow, so you have to use 30, 32 extra steps to have something quite nice in terms of vision. So what I can do instead is to say, okay, I have a pyramid, and I have a maximum number of iterations to do for a pyramid, for example, because at some point I don't have much to compute, so that's also a trade-off. And I can chain the pyramid like this. So I have less intermediate computation here because I reuse the cache as much as possible here. And the last, maybe it's a bit smaller because it's the last iteration, so I can do the full pyramid. Of course, I have to stop where it's needed. So here you see I reuse as much as possible the data inside the pyramid. So I compute the same, but I use much more efficiently the memory, which is what everything is about right now. So here you have a number of iterations, but a number of iterations of pyramid, if you want, not the full as before, quite different. So we can have a first algorithm to do that. So I get all my blocks, I perform my pyramid, so I shrink in the future my pyramid. So I do that for all the blocks at the same time. So of course we can parallelize also on it. And then I have to finish the work for all the other parts. So I can say, okay, let's change it. Let's shift a bit all the pyramid for this algorithm. So I stay in the same memory. And then I can say, okay, let's do a cross and go up with a cross like this. So I have a cross and I expand the cross to fill the missing gaps in the pyramid. So it's 2 algorithms to fill everything, and it's quite a bit too much. So we do that for the 2 in the middle here. We do the same for all the borders here, so it's quite heavy and tedious to do, of course. And there is no explicit communication with this pattern, so nice. But of course, you have 2 algorithms to put together to be sure that everything is working, and that's quite annoying. So in terms of blocking pyramid, we have this kind of stuff. So I go in the future like this, and then I can go back with the rest of all the computing like this. So quite nice. In terms of parameter, we have to play a bit with the parameters. So you can say, okay, if I have L1 cache, I have a small pyramid. So I cannot go in the future much, but it's really fast in terms of read. But if I have a larger pyramid in L2 cache, for example, I can go much in the future, but with a bit slower data access because it's L2 and not L1. So it's a trade-off again. And the same if you go too far in the pyramid, at some point you don't have much data to vectorize, and the vectorization is way less efficient. So again, other parameter to play with. And maybe if you have a question on this path, because here it's the end before the next talk. Yeah.
Why T equals 2? Why at T equals 2 we shrink of 1 pixel on each side?
Yeah, because I want to reuse the block as much as possible. But the problem is the block is inside the bigger image. If I want to update this block only without the knowledge of what's going on around the block, I don't have the information to update the very border of the block. So I cannot update it. I cannot use it and say, okay, I don't know what's coming here, but I assume, no, you don't have the information. So you have to say, okay, the very border of the block, you cannot update it because you don't have the information. But the border inside it, you can, because the information for one step, you spread the information of 1 pixel. So for the future, you can say, okay, I just take the inner block 1 pixel, I go in the future, and then once again, and you build your pyramid like this.
Because the information always depends only on the pixels side.
Yeah. That's the trick. That's the trick of Sebastian. Because nobody can think about that, let's be honest.
Maybe we can add something just to explain a bit more clearly. You cannot compute the neighbors because to compute one cell, you need the cells around it. So when you're on the border of your domain, you don't have yet the next data. I mean, if you make multi-threading. So you are forced to reduce the part you compute, and you will be able to compute it later. But this is due to the stencil we have seen the first day, I mean yesterday.
Yeah.
Yes, you mentioned non-explicit communication. What do you mean by that? Intuitively, I would imagine you have to sync the information between the blocks after you do the pyramid.
Yeah, that's a big problem. In fact, that's why I have a second presentation about that. And that's a really good question, because that's a very big problem of the algorithm I just showed you now. It's once you are performing the pyramid part, the first part of the algorithm, it's okay, because everyone is independent, so no communication, it's okay. But once you want to make the anti-pyramid computing, you have a problem, because here, if I show you this stuff, this one is more clear. Here, I want to compute the anti-pyramid here. So here, everyone is in the past, and I try to get them in the future step by step. So this means that this to be computed in this block needs to have the information of this one. So these are to be needs to be perfectly synchronized. So the problem of this algorithm is you have a full asynchronous pyramid, the first step, the blue step. But for the orange one, you need to synchronize everyone at the same time to get them into the future. And that's a very big problem. And of course, you don't want to do that because in synchronous, it's better for scalability. And that's why it's a really good transition, except if there is other question. Discord, where is Discord? Discord? No, no Discord. Discord here, Discord, okay. Discord. It's me to work on, Alessandro says it's me to work on a stencil calculation. Yes, but that's an answer. Question from Lucas. This concept of cache pyramid optimization is only for stencil, or I am missing something? It's mainly for stencil. I'm pretty sure you can use it for other stuff, but it's less problematic. If you don't have a stencil, you don't have the problem to spread the information with the neighbors. So normally you can go straight forward and say, okay, I iterate. We will see that next week also. So that's really interesting to have for the optimization if you need some neighbor information. Otherwise, normally it should be quite straightforward to do it. So you can also iterate if you have an iterative algorithm and you don't care about your neighbors. You can also iterate a lot of time for the same block to say, okay, I compute this block once well, and then I compute the next one, etc. But here, the stencil makes it more interesting. But of course, you can use it for other stuff. For example, for the computing, I will show you next week, but don't spoil too much. But yeah. So let's try to have a better algorithm, because this one is nice, but horrible to write, of course. So we want to do something a bit simpler. So let's rethink about this problem. So we want to reuse data inside the cache. So how to do that? So I can say, okay, one stencil, here is a 3x3 stencil. So if I have a block and I want to go one step in the future, I have one border of information. I can go inside one step in the future. But if I think differently, I can say, okay, but if I have 4 steps in the border, I can get 4 steps in the future for the computing, because I don't have to share the information with all the neighbors or all the blocks, let's say, or neighbor blocks. So the block have to be large enough, of course, otherwise the border will be a bit too big for the rest to compute. And so here we can say, okay, we have one block, and we can compute this block, so 16 per 48, so 768 pixels. And the ratio is 75%, so with a border of 4. Okay, obviously it's not too much. So let's do the computing just to see. So if I have a certain size of border here, with a certain size of number of pixels, so the width of the pixels. So if I have 1920, should be somewhere here. So I can have the evaluation of the number of percent of the, which represent the border of the block, to see if I use much more memory to go in the future. So here, with a bit more than 2%, with 8 border block, I have 2% of my memory. I increase my memory of 2%. So I do a bit more computing, of course, because I have a block. I use the outside of the block, so to overlap with other blocks. And everyone is computing the future. So I have a bit of more computing, as we said in the lunch time, of course. You can do extra computing to avoid communication. That's exactly what we do. And here, what we can do, it's, okay, we have the input of the image we want to compute. We have the temporary part around it, so the tiles, if you want, around it. So we will exchange probably this tile in the future. Come on, please, now. And then we have this border. We have the temporary output, because once we update the input, we get a new output as before, input-output as before. And then we have the naming here, north, south, east, west, east, this kind of stuff, to just get the tiles, the proper tiles for each block, to be sure that everything is nicely done. So in terms of data exchange, to compute, so we can compute all the parameters separately, because we have redundant computation, so all the parameters can go 8 steps or 16 steps in the future at the same time. So it reduces a lot the number of times you need to synchronize everyone to get information. So that's important, especially if you do parallel computing. And then I can say, okay, all the neighbors will give me the new values of my border. And then I will also give to everyone the new values of my border for everyone to get the information. So of course there is a redundancy, and you can manage the size of the border to get more performances. So that's also a trade-off, because if you have a bigger border, you compute a bit more. You have to exchange a bit more information, but you can go more in the future. So that's always a trade-off to play with. So in terms a new view of this one, so you have the full temporary data, so input and output that we will use for the computing. Then inside we have the output that we will compute during the time with the border. Then we have the input of the neighbors, so extra neighbors of these blocks, and the output to the neighbors, so for the neighbors. So I will compute my my output, and the border inside on my output, I will give the output to my neighbors, so everyone is sharing the same information here. So basically, I get my input, I put my input into the temporary input, then I roll my my 32 iteration with, or if I get a border of 32, if I get less, it's less. Of course, 32 is nice, but you can do 8 if you want. The only thing is to have the same border for all the blocks, otherwise you will have some problem to synchronize everyone. Then you put the TMP out into the output, and you share the new output, the neighbor output, to your neighbor, and it's okay. At the same time, you can also update the input, because if one of the block of your neighbor block finish its computing, it can give you in another buffer the result of the computing, so you don't have to share it. The first which finished gives the information to the other, and etc. etc. You don't have to synchronize explicitly. You get the information as it is computed. So in terms of transfer, if you want the story of the transfer, we get the thread 1. So I compute the frame of the first frame, frame index 1, for example. And for it, maybe I need the thread 2. Thread 2 is in maybe maybe a more extensive computing core, a smaller machine, something like this. So the thread 1 is much faster than the thread 2. So when it's finished, it updates the computing, the input for the thread 2. The thread 2 is rolling, so no problem. There is no conflict here. And of course, the thread 1 cannot start to compute the second images until it gets the information for the thread 2, if they are neighbors in the memory. So of course, we have to wait a bit because we cannot compute if we don't get the information. And for the thread 3, it's the same. Maybe the thread 3 is a bit late also, so the thread 2 will wait for the thread 3, but the thread 1 will compute the second index, start to compute the second index of the image, even if the other do not compute the same image. If everyone is synchronized at the end, it's okay. And then it's a bit different. Here, I'm ready for the thread 1 to compute, but the thread 2 didn't start yet the computing of the second image. So we will have a conflict if we exchange data too quickly. So we have to wait because the destination is not ready for the new input. So we have to wait a bit. We have all these scenarios here. And to finish, maybe thread 4 also have to wait a bit, and you can have a pyramid, a temporal pyramid inside your computing. So it's kind of in simulation, solid simulation, stuff like this, you always have this kind of growing simulation inside the solid, inside network, this kind of stuff. So that's the kind of stuff that we will discuss today, and that's in terms of implementation. So that's that's what we will discuss with Sebastian just after that. So we have device data, so the kind of container that we will use to store the tensor, so really raw tensor as a SED vector if you want. Then this is based on a resource memory manager, so kind of allocator, custom allocator I showed you before, but the memory manager is capable also to do some data transfer instead of only allocating or deallocating data. So we can allocate, we can move data from a CPU to a GPU, this kind of stuff. So that's a backend. Again, design. I want flexibility, so that's only a backend. And if I make it smart, it's okay. If it's not smart, maybe I can do some stuff and maybe I can improve it later and change the backend later. On top of it, we have the tiles, so the border of the block to change everything. And then we have the pyramid to do the computing of everything. And the meta image to get, if I get a really big image with a lot of pyramid in it, to be able to deal with it on CPU, on GPU. And then I can stream my tiles in the computing, this kind of stuff. We'll see that also next week. So in terms of tile, I got my Grayscale reaction here. I split it into a lot of tiles because I know my network, I know my computers, I know everything. And then I can stream all these tiles to whatever I want. So CPU, GPU, several CPU, several GPU. So I break down my problem into something which is simple to deal with. And with the border, with the trick of the border, I have less synchronization to do because, of course, doing a full synchronization of full rack or full blade server each time, so practically 1,000 times per second, of course, it's too much. It will kill your network if you do that. So you want to have some tricks to limit this kind of stuff. And that's it. And I will give the floor to Sebastian, which will explain to you also implementation and a little demonstration of what's going on also.
Okay. There is some question already in the Discord. So we'll look on my implementation to answer the question. Probably it will help to understand. I will explain again my view on these algorithms to have another view with more animations, and we will go to the implementation details to understand how we can implement this. Just one thing to be clear, the blocking is very important when you are doing computing because you need to use the CPU. The pyramid is a more advanced thing. Probably you don't want to do this one in a real code. This was here to show up to where we can go by using the caches of the CPU. But the basic blocking is relatively easy to implement in practice, depending on how your code is done. This is important to be done in a real code. I will start my slides. So we need to start again the virtual machine. So blocking from the point of view of a memory management guy, let's say. So just to remember to the basics, what we want to do at the beginning is that you remember the cache hierarchy of the CPU, okay? We have on Grayscale an HD array, which is 1920 multiplied by 1080 for the grid itself, plus 4 variables, U1, V1, U1, U2, V1, V2, if we compute not in place, which is my case. So 4 elements, and this is some float, because I'm using floating points, 4 elements, so it takes 30 megabytes. 30 megabytes. If I take the cache of my laptop, the cache of my laptop is currently, sorry, I don't have any more animation. It's roughly 8 megabytes, something like this, what I have in my system. 8 megabytes, we have 30 megabytes. It don't fit in the L3 cache, okay? So our goal will be to avoid the threads to fight to access this L3 cache. This is what we want to optimize here. And by making the blocking, what we want to do is to say that each thread is working in its block as most as possible. So it fits in the cache, in the L3, in the blocks it's working on, as most as possible. Of course, at some point, it will need to move to the next block and feed again the L3 cache. But if we are working like this, we don't have a conflict in the L3 cache when we are parallel. Because if we are sequential, if we have only one process, not the black one, of course, I can use my cache hierarchy a bit in a simpler way. But I'm not using all the cores of my machine. If I'm using all the cores, I will stress a lot the L3 cache because all the cores will attack it to ask for some data. So the problem of the blocking is not arising when you are making a sequential program, but more when you are making a parallel one, because your CPU is not fed by the memory. So for the L1 blocking, the basic solution is to make some square. So you can make some basic blocking on the L1 cache, as Pierre has said. This is what we call tiling in some languages, depending on how we speak about. Notice one thing Pierre has not told is that the boxes you are taking here to make the blocking, ideally you should not take them squared, but a rectangle, because you know that in your mesh, for example, you are contiguous. If you are depending on the axis you are contiguous on, you want to make the more computation as possible on this axis. Because when you arrive to the end of the box, you interrupt the CPU to enter to the next loop and come back to the beginning, which interrupts the prefetcher. Because when you are here, the prefetcher has started to take the data on the right, which make a little bit loss of performance in practice. The prefetcher, I didn't explain yesterday. When you access one data, the prefetcher of the CPU is taking the next part because it supposes you will access it. It starts to take the data in advance in practice. Yeah?
I've never thought about that. How much impact does that have? Like to actually block it like this?
You mean what is the rectangle size, which is okay?
No, to yeah.
You can play with some factors. It depends on your problem, of course. Myself, I put a factor 2, something like this, to get a rectangle which is 2 times larger than I.
Okay.
But this you have to test for your problem and your architecture in practice.
Okay.
You will see in my code, you can play with a parameter. You can check which one is the good one. But by experience, it's better if you take a longer element on the axis you are contiguous on, because you get the prefetcher, the vectorization, and everything. If you make something squared, you penalize the bits, the vectorization, and all the things you have made this morning, sorry, will be penalized. So when you make the blocking, you have to think a bit about this part you made for the vectorization. So ideally, to take some rectangle box. If you take care of this, you will improve a bit the performance. So the boxes, of course, you can select either to make them fitting the L1 or the L3 or the L2 cache to be efficient in parallel. So how to do that in the code? Because at some point you need to implement it. This is where you remember yesterday I spoke about unit test, etc. If you don't do unit test and you try to code the blocking by hand in your code, so the blocking with just some simple box, it's quite easy. If ever you want to go to the pyramid, no way if you don't do software engineering, because just playing by indices, you will be killed quickly. So in my code, I splitted the implementation sorry, I made a typo. I made an implementation with 2 stages. I have the kernels in one part, the thing you have studied this morning to optimize, just the loop which is looping on a rectangle of my mesh. And a scheduling part where I can implement different scheduling, a basic one, which is just looping in one go in the full mesh, making the L1 blocking, the L2 blocking, L1 pyramid, L2 pyramid, etc. Okay? And I try to make this way that, of course, as a scheduling part, I can unit test it. This is very important because, of course, I will make some mistake when I will implement my blocking, and I want to check this automatically. So in terms of code, the way I'm making it myself, we will probably try to look a bit more in the code itself after that. But just to get the semantic, I try to hide the details of the blocking in one class. To make one class, which is my basic blocking basic, class, which is here. For where I pass the data model, this is something which declare, I will show you after that, to list the variables which are inside my mesh to compute the size of the rectangle, the rectangle on which I'm computing on. So there I tried, when I make an implementation with the blocking, I try to make some rectangle box. So in my code, I implement the things like if I'm drawing the box on a paper. Because otherwise I will miss myself with the indices by making some mistakes. I have my kernel class to change the kernel, and then I have an iterator on the L1 basic block to iterate over all the blocks. Okay. The good point of this implementation is that I can unit test it quite easily. I can make a unit test. I will show you after that about my blocking thing. And in the real code, I just call my kernel with the data block, the block size, a rectangle which has an indices and a size. Okay. If I want to parallelize, make some OpenMP parallelization, now I just have to put an pragma OpenMP on top of my blocking iterator here. So my blocking iterator is returning all the blocks. The blocking iterator is just producing, the block here, the block here, the block here, etc. Okay, this is exactly the class I provided. The class itself is not necessarily easy to implement, but once you have it, you can apply it everywhere in every program you can use. If I want to parallelize, I just have to put a pragma OpenMP parallel for on the blocking part, so every thread gets a block and work in its block. Okay. We will look a bit more in the code when I will show you the demo parts. Why it's blocking. So for the pyramid itself, same approach. We make some rectangles and I compute the pyramids inside the rectangles. The only thing is that we need to make the phases that Pierre has explained before. The phase 1, which is making the big square part. I don't have any more my cursor. Okay. The phase 2, where we make the top border, the bottom border, the left border, and the corners. This I will show you in a more interesting demo after that. Yeah, this is exactly the same thing I said. We make the big border. Sorry, let me explain. We make the first part in the middle as the first phase. So I have some phases in the code. We will see. We will have a loop about the phases. Phase 1, phase 2, we make the top border. Phase 3, we make the left border. And phase 4, we make the corner. Okay, you see that there is some missing here because here it's made by the block on the other part. The next one, the 9 ball. In your implementation, if you want to play with blocking also, but mostly the pyramids, at some point you need to manage the border of the mesh, where your pyramid is growing and is going outside of the mesh. So you need to make some intersect semantic in your buffer, in your rectangle. So you finish with a pyramid which is implemented that way. So this is exactly the same implementation than before. I have a pyramid blocking, which is my class, which is computing the pyramid blocks. I give him the data model I have, so I will show you it's the list of variables I have in my mesh to compute the size of the block depending on the cache size. I have, where is my cursor? The rectangle on which I want to compute on, and the size of the cache I want to make the pyramid in. So this class is responsible of making the pyramid implementation. This class is hard to implement, but once this is done and tested in terms of unit test, I'm sure it's working well. I can put it in my code. This is why yesterday I was speaking about unit tests. If you want to make complex stuff in a software, if you don't have unit tests, you will fall in some troubles with your software. So then I have the first loop, which is the, sorry, I don't have my cursor. You see it? Yeah. I'm looping on the phases, phase 1, phase 2, phase 3, phase 4, for the center, the border, and the corner. I'm making the parallel loop, and I'm computing the root of the pyramid, the one which will serve to compute the pyramid. And I'm making the forwarding steps here to make the step 1, step 2, step 3, step 4, step 5. Okay. And again, I'm calling my kernel sequential with the block I have computed to make my pyramid. So the pyramid, again, this is a bit very advanced steps which probably you will never do in your code. But we will see in the demo that we win a lot of performance with that. This is to see how far we can push the thing. Okay. So for you, remember the simple blocking part with the simple rectangles. This is what you might implement in real life in your code. Okay. The pyramid, clearly, this is a bit to show up to where we can go with the philosophy of blocking. So we can do also different scheduling. So making a pyramid in the L3 cache this time, so a bigger pyramid, and an L1 blocking inside the threads. So we can compose like this the blocking strategy in some ways. So it makes the code a bit far more complex, but we can do everything we want by playing with the hierarchy of the cache. So my goal here is not necessarily that you remember exactly how we make the thing. For example, it's a unit test here, a unit test of the pyramid. I'm creating a matrix here just to show a unit test on a real example to see how in real life it lands on. So I declare my test pyramid blocking, apply sequential phase with 3 forwards. So I'm making a pyramid with 3 steps in future. So I create here a matrix 20 by 20. I create my rectangle, which is, I get the rectangle of the matrix 20 by 20. I fill my matrix with some 0 to initialize my matrix. And to make my test, I create my data model. We'll show later how it is implemented. I add a variable to my data model to say I have one matrix, because in my test I use only one matrix, with some floats. On the 0, we don't care about this argument. This is the ghost cells if we have some ghosts. And I call my pyramid, and inside, as before, the phases, the root, the forward, and in my matrix, I will increment. I will take the rectangle of my box and increment by 1 all the elements of my matrix in the block. So the goal is to see at the end if my matrix is fully covered by the elements. So I can compare to a matrix which is filled by 3. I expect a value 3 at the end for every cell, because I made 3 steps in advance by making +1 for every step. And I check by making an assertion here. Assertion, matrix and equal to matrix ref. And I display a diff if ever they are not equal. So to debug, I get the view of how it is. So this is to show a real unit test, a bit in a very complex case. So most of the time, your unit test will be a bit simpler. But to show up to where we can put the thing, to validate here a code which is relatively complex. Okay, in real life, this is how it looks like when you are making a unit test on an advanced thing. So now we can move a bit to the demo. So for the demo, there are some questions. Yes, the pyramid concept. The pyramid concept is to say, I want to use, we made the blocking. The blocking, sorry, I will take a picture to experiment. I came back to the parts. I remember the goal. The goal is to make the blocks, to use as much as possible my blocks. Okay? If I fetch my block once, make the computing in my blocks, throw it away, take another block, computing in my block, throw it away, take another block, computing again in my block, I will require a lot of memory transfers. Okay, already less than if I didn't make the blocking, but still a lot. The goal of the pyramid is to say that if I already get a block in my memory, why not making several steps in this block to reuse it as much as possible? Okay, so this is exactly what we have here. Well, I will show you an animation. You will probably understand a bit better. I don't make the animation here. Let me show the animation. My connection has been cut. So if you go to the Great Scott School, we'll see the gain in terms of performance, and you will see it's not nothing. I will just restart so you will be like you. So for the people here, you can go directly to the Jupyter Hub, go to Gray Scott 2026, and taking the profiling memory. Everything about memory I will speak about this week is in this container, so you can take it. For the people online, you can take the container, which is here. I will put the link in the Discord. So the container itself, if you want to take the one with VS Code, you just use this one, which is a code server. Okay. So you have everything in. And for the people who really want to use it outside, you can also clone this repository if ever you want, but you will need one dependency, which is HDF5 and probably libImageMagick++, because this is what I'm using for the rendering. You can clone in case someone wants to make native. So for the live example, I will come back to this, reload my window, launch my server. Why I didn't launch? Starting the container. Okay. So if you go already in sorry, I close this. When you arrive in the container, you arrive like this. You go to free-grayscode-mem, which is where I have all my my code. And in CPP, we will use the C++ version because I'll provide you also some other implementation in Python and in the Node.js. I tried to make the pyramid in both. So I will put for the one online the path. So everything will arise in, no, not the same than this morning, another one, sorry. Memory container. Okay, so if I go here to compile the code, I need to create a build directory because I'm in CMake. Sorry, I forgot to zoom. I said to Pierre to zoom and I didn't make it myself. So I go to Grayscott memory, CPP, and inside this directory, I'm creating a build directory. I'm going it. I will put the commands in the Discord just after that. I do CMake CMake build type equal release because I want to compile it optimized, of course. And sorry, dot and make. So I put the command in the terminal. Alors, sorry, I'm writing to use the commands. This is taking time if I'm doing that. That way. CMake equal release dot make. Pour le Discord. Can I zoom the Discord? Yeah, I can zoom the Discord. A bit too much. Can I dezoom? Yeah, okay. Anyway. So it's compiling. So here you see there is several binaries. The one we will use is pyramid, which is a simple program to dump the pyramid blocks. So we will be able to display them in a small web page animated to see how it is building the blocks. Okay, so I will use that for now to understand how the blocking is running. So I just call pyramid. It's producing a pyramid.js file, which I can load with the. There is a debug pyramid.html inside the directory where I can display it. So sorry, if you are in the container, you need to python that m http.server hd some CMake error. You need to create a build directory before and go in. You don't have? Yes, there is cmake.txt. So Joseph, in examples, you don't have the cmake list.txt. Where are you? There is someone answering. Demo effect. All the time demo effect. CPP. Sorry. So you need to be in the CPP directory because there is several implementations in my directory. So now I will just expose, because I'm in the container, and will just expose the file. Python free. I will give you the command, just I want to show before. So here I made a small HTML, because when you make something complex, always think how I will debug it, because for sure you will make a mistake by making your implementation. Okay. So for the pyramid, I made this kind of. I run it in parallel. Let's make it in sequential first. OMP num threads equal 1, no threading. Otherwise, it will be complex. Where is my page? Here. I will give you the command in a second in the Discord. So just to show here, I have this debugger where I can play step by step with the rectangle on which I'm the blocks on which I'm computing. Okay. So first block I'm taking a small block on the top left of the mesh. Next block, I'm making the pyramid a bit inside. Next block, the pyramid a bit inside. Next block, the pyramid a bit inside, a bit inside, a bit inside, etc. until I get the end of the top of my pyramid. And then same thing for the pyramid aside. You understand that as my block fit in the cache, while I'm working inside this block, I'm not accessing to the RAM. Okay, so I will be a bit faster than accessing all the time to the RAM to request the data. So of course I will do the pyramid for all the blocks. So I can do the first step of the pyramid. And you see, of course, that there is some missing points because I have still some parts which are white. So I need to fill them by making the pyramid in the other way. So I will go to the end where I am. So you see on the border, there is something in the algorithms which is not simple. The box on the border is a bit smaller. It's cutted on the border on the mesh if it's not a multiple size of the mesh. This is where the implementation is a bit tricky to do. Okay, so this is why if you don't do unit test, don't do that because for sure you will be stuck. So next stage, I will zoom a bit. I'm making the border on the top. Okay, so I'm making the border on the top. Border on the top on the other one. Border on the top of the other one, etc. Border on the middle, so top of the second line. And I'm filling like this all the elements. Okay. Now it says to make the border on the left. You agree? So I will do border on the left, where it starts here. So here I made it in a non-optimized way because I made it block per block, but I'm making the pyramid on the sides. You see some holes still. I need to make the corner at some points because I will fill in the second stage on the left part all the blocks except the border, the corners. Okay, so at some point I need to make the corners and to fill the corners until the point I have made all the steps of my mesh. Okay. Now, as I said, I want to do this in parallel. So I will take again. I zoom a bit too much here. I will run again my pyramid to generate again, but with threads. Let's say it's 4 threads. Okay, 4 threads. And I will just load again my viewer. I will put you the command in the shell if you want to play with that. Now, if I make play in parallel, I see that some of the threads are starting, of course, to make each part of the work. Okay, I have 4 threads running on the blocks. So some blocks are starting in the middle of the pyramid, and we fill like this all the pyramid. This is the parallel things I'm doing. We can make it in color to see, enable color, to see the color of every thread having a color where it lands on. Okay. So this is how I try to get also some locality. If you take care, I mean, I try to make such that the threads which are neighbors are working on neighbor box. Otherwise, it degrades a bit the performance. So again, the pyramid, this is a very advanced thing. If you made already the blocking, the naive blocking, you can do just the blocks. While the ranges overlap. So Stevenson, the data ranges overlap. I don't see can you precise your question? Because the ranges, they don't overlap because I don't want to compute 2 times. I have several threads computing at the same time, so I don't want they compute at the same time on the same data. This is why I have these phases. If you take care with the phases, let me, if ever you want to play yourself, I will give you the protocol. So once compiled, run threads equal 1/pyramid. There is no overlap at this time here. Every part of the pyramid is computed in a non-overlapping way for every threads. So you can play like this with the pyramid. So I didn't play here the fact that I'm making some more complex things, the L3 block and the blocking inside. You can display also this thing with my code if you play a bit with some advanced thing. Now we can look on the performance to understand that it rise up something. Where I am. Terminal is here. So now I will play with run. This is my main executable. If you run --help, there is a question on. Pixel packet is not defined in. Where are you running, Luc? So when you're in VS Code, sorry, I should explain. When you're in VS Code in the container, when you are launching the Python server, control click on the address because it's redirecting you to a kind of proxy to display the page, and you need to open debug. Does that answer to the question, Joseph? If you are local, you can access the port directly, but if you are running elsewhere, I made a space between. Sorry. Yeah, thanks. I should have copy pasted. So this is if you want to play yourself to understand the algorithm, to see how it's running. Again, when I'm developing something complex, I say to myself how I will debug it, so I want to be able to play with it in a visual way. I'm something visual. I prefer to visualize what I'm doing all the time. This is very important to understand what I'm doing and to explain also to other people what we do. Performance. So as I said, now I want to play with run. So if you look on the help of run, you see that there is several options. I mean, a few. We'll play with essentially the optim options, which select the optimization I want to do, L1 blocking, L2 blocking, etc. So you can -o help. So here you have the list of optimizations I implemented in my code. Okay, so either the sequential naive way, SEC, the sequential with L1 blocking, sequential with L2 pyramid, L1 pyramid, L3 pyramid, and L1 blocking inside the pyramid, and all the combination we can construct that way. So we can try to play a bit. -o sec. We will start first with the sequential version to understand. I give the command for the people online. If I'm using sec, it's running. So I don't know if I'm alone on the cluster. In case I will have another one to back up. So I'm running at something like, so it's not really stable. So probably there is some people running also at the same time on the machine. And I zoom too much. I have 4 in median. My median is 4 cycles per element. per iteration. Okay, 4 cycles. Now I will do L1 blocking. What you guess? Not very good. I mean, at least it don't look like. There is some lag on. Okay, so I will wait a bit, the people online, to not lose them. Thanks, Luke, for saying. For the other, you can play with the different versions, with already the sequential version to see if you win something. Play with the various variants. You will see probably something. 7. I made the blocking. Come on. Let's say L3 pyramid, L1 blocking. I wait a bit. I wait a bit the others. Come on, I made some work and I have something slower. That's all the time. When you make optimization, sometimes you make some assumption and you finish with something wrong. But we will see that it depends on the conditions. So maybe also the server is saturated because if everyone is downloading the image at the same time, we are a bit. I will prepare in another server in case where it is. Here I will be alone. Just to be alone on a server to make sure for my measurements, the one where I validated. So while waiting, the others, you finished to get the image, Luc? .5 and 1 blocking. So here I'm on another server where I'm sure to be alone. Not have someone killing my measures. Yeah, also free something. Slower. You made blocking and it's slower. Pierre, you lied to us. No, we'll see it's not a lie. We'll see where we gain. In practice, I'm on a big server. This is a server who has how much of memory in my cache? ls topo. If you want to look on your cache hierarchy, you can use the ls topo command. I can give you on the chat. ls topo, sorry. My cache is 32 megabytes, my L3. If I look here, my L3 cache is 32 megabytes. I say, what is the size of my mesh? You remember? 30, huh? 30, so it's smaller than the L3 cache. Because we have a problem which is so small on this big processor, my cache is big enough to fit the problem in one go. Okay? So my cache blocking is kind of not efficient because I'm already in the cache because my problem is too small. Okay, thanks, Luc. I hope you will get access to the thing. So I will try to make the same run by adding -r, and we will run in a 4K. We'll increase the size of the problem, so it will be a bit slower. Still 2 cycles, something like this currently. Maybe I should make something shorter. Less frames. Same execution, I reduce the number of frames I'm computing. Okay. 2.49. Okay, so now I do L1 blocking. So the histogram is the histogram of the, yeah, sorry, I should remove it. This is more for funny things. So this is the histogram of the distribution of the iteration cost. The things that Pierre has explained this morning. 3 cycles, still slower. Come on, I took a problem which is larger than the cache. I should have win something, no? How many threads I have? No, I'm running sec. I'm running the sequential version, okay? 1 core. I'm using 1 core on a big processor which has 32 here. Do you think I can saturate the memory of the processor with 1 core? Probably not. The processor is tuned to feed 32 cores, so it has enough bandwidth to feed 1. So here, of course, by running with 1 core, I'm not saturating the CPU. So let's move to OpenMP. Let's keep the 4K. OMP. Faster. 0.74. Okay. In OMP, naive, without blocking. Now we'll say OMP L1 blocking. There is still the error about, I will come back to you. Already, I win a bit. You remember it was how much? 0.74. By making the blocking in parallel, now I'm at 0.34. Factor 2? It's quite nice, a factor 2. This was a lot of effort to get it. I mean, this is a simple blocking. The simple blocking, remember, you can do it yourself, this one. The pyramid, we'll see again, but it's more complex. But already, by taking care of the cache, I can win a factor 2, at least, on my simple case. On a more complex case, it can be more. Let's take the L3 pyramid. L3. I will come back to the remote PQ questions after that. L3 pyramid, L1 blocking. So I'm making a pyramid on the L3 cache, L1 blocking on the inside. Not very good. Where I am? 0.8. Close to the naive version. Let's try another one. L2 pyramid, L1 blocking. This one I need to reduce the number of forward steps I'm making. 0.19. Again, not a factor 2 again, but how much? We pass from 0.30, 1/3? 1/3 of the performance gain? This is quite cool. So quite cool, but the amount of effort to get the pyramid was, compared to the naive blocking, clearly a lot. Okay, so we start to see a bit where we are on the limit on the CPU, on what we can do. But I will discuss another thing after that. We can see that in some cases we can win far more. I will show you. Before I will give a look on. This is Magic++. You are compiling, Leon. Who is posing the question about this? Still compiling on a laptop. Probably. This is in Docker, Leon? Or this is on your laptop directly, the ImageMagick thing? Because, yeah, I have a portability issue. Depending on the Linux you have, ImageMagick has a different semantic. This is not the same version on all. So I have the code for all. You need to change one line in case. Yeah, locally. I can give you the file to fix if you want. src lib rendering, no, dump ImageMagick. So for the people who want to run on their laptop with a different version of ImageMagick than the Ubuntu one, the Debian one, sorry, you should go in this file and change the diasif files to true, or the invert. I forget if it's sorry, they broke their API in ImageMagick, and I don't made an automation to detect it automatically. I have both code, but you need to switch by hand. So came back to the measurement. Here, some people succeeded to play with the code here. Fine. Wait, what time it is? I have to just remember the timings. 15h30, donc I have 10 minutes. Cool. I will be on time. I take back my slides. So this is a perf we just show by hand. Yeah, I can show the number. With the pyramid, you have to choose the number of forward steps you are making. How many steps you go in the future in one block. So you can make some measurements for the L3 or the L2. How much steps is the most optimized? Of course, it depends on your architecture. For me, on the processors I was running on, 30 or 29 is the best I can get. So 30 steps in advance in one block. After that, the top of the pyramid is too small, and it starts to cost too much to compute the boxes, etc., for nothing. But so you can say, yeah, I fooled you a bit because we make a very complex thing to win just 30% of performance. Already it's 30%. Huh? Some people with the vectorization, you fight a bit more to get this gain. But what I compared. Up to now, I compared either 16 threads in OpenMP with a cluster which is full with one task. Okay. But what if I'm running several times the same job? For example, in particle physics, they have a lot of sequential job to run, not parallel one. And here I was comparing the OpenMP one, so trying to make parallel my small case in a big processor. So probably there is not enough work for every course to do. So I can compare the other way, trying to run not one task sequential, one task parallel, but several tasks sequential. You see what I mean? In some ways, I want to do, instead of having instead of making a large run on my cluster using all the cores, I can make several runs sequential on the same machine. So launching my run program 32 times. You see what I mean in parallel? For example, for some people having to make in particle physics, they compute for one collision, making a run, making another run for another collision, making another run for another collision, and they launch all those jobs which are totally parallel in the machine. What is RK? -R resolution. So 4K, this is a resolution in terms of video size, video convention. Dash S, this is dash step if you take the number. So dash R is the resolution you want to use, and dash S this is the number of steps you want to compute, which by default is 3,200, something like this, which I made to 1,000 for the test. So if I want to run in parallel many jobs, there is a small script here, which is launch many. Launch many, if you look on the thing, I can say how many jobs I want to run. I will say 32. Okay. And how many I want to run at the how much I want to run in parallel. I will say 32 also. So giving one core for every job. Okay. That's /run -o. I can say optimization sec 1000 and -r, let's say it's 4K. I forget this. I had to this terminal. So I launched several jobs. Maybe this is too short, what I know. 100, 1000. 64. No, 32, this is okay. So 32 jobs running at the same time in the machine. 20 cycles. This is a sequential version without blocking, what I'm running. Roughly 22, you see that it's not really stable also. The jobs are fighting for the cache. We'll see at the end the result is varying a lot. Maybe I can reduce to say 400, it would be enough. 900, not to wait too much. $11 seconds. So we see that globally we are going to, this is a bit too short what I made here. Let's make longer. So we see that when you have several jobs fighting in the cache, some are winning, and this is a battle. I'm taking the cache, you are taking the cache, I'm taking the cache. No, this is for me, no, this is for me. This is a battle on the machine. So now we use OMP, L1 as sequential, L1 blocking. Okay, so normally less fight in the cache. Less, but still. So 15 seconds, you remember? 1570. Still some fight, but looks a bit smoother. Joseph, this is on your machine? This is with Pixie. So with Pixie, you need you can replace user. I mean, you don't care in practice. If this is running, you don't care about the error message. $19 seconds. Yeah, longer. L3, pyramid, L1 blocking this time. Okay. 2.8. 5 seconds. 2 times faster. Okay, in 4K. And I am on a machine which is a bit, I don't run long enough in practice. So I can show you some results I made on a real machine with 64 cores. Where it is, the 64 one. So with the problem size on a real machine, because here I'm in a virtual machine somewhere else with 32 cores. Sorry. Page history after that. Yeah. Let me explain this and I will come back to you. Here I'm comparing several versions on a 64-core machine, so a larger machine and without a virtual machine underwood myself. And you can see the speed up between the sequential version and the sequential version. You run in parallel. The one I running 64 jobs at the same time in parallel. So you compare the yellow box with the green one. Okay, so you can win up to a factor 7. And if you increase the size up to 4K or even 8K or something like this, it can go up to a factor 12. Okay. You see that the OMP L1 blocking is not so far, but still a factor 2 slower. So we gain a factor 2 by comparing to the OMP. Sequential OMP is OMP L1 blocking easier. Sorry. Sequential L1 blocking, I don't have it. Sequential L1 blocking is easier. Sequential L1 blocking, as it's not solving the problem in the L3 cache, it's not gaining for the large for the problem which is not fitting in the cache. Okay, so the pyramid is winning at some point if I'm stressing a lot the machine. If you don't stress a lot on your machine because you have a small problem, no way to make the pyramid. It's not useful at all. Okay, but the win you can have is a factor 12 here. Find another way to get a factor 12 in your machine by making vectorization or something else, you will fight a lot. So you see that the impact of the caches in your performance today is quite important, depending on the way you run on. For OpenMP, I'm not winning as much as for the parallel sequential version, because for OpenMP there is some synchronization, and we are not making enough job, so the threads are not to discuss too much together. Okay. So we'll stop here for the pyramid because we are out of time. Maybe some question on the Discord. Could you paste his no, this is for the comments. You, Isabelle. Where is Isabelle? Ah, sorry. This one. Thanks, Joseph. Let me take the command. So I'm comparing this L1 blocking and this sequential. Any questions about the blocking? Yeah.
On the histogram you showed at the end, where can we see the sequential on multiple? Is there a way to compare the thing you mentioned last, the sequential, but on multiple jobs at the same time?
You mean sequential and one parallel jobs?
Is that the OMP?
Yeah, this is what I'm doing here. If you take the OpenMP one, I launch also 64 jobs, but one job taking all the cores, launching another one taking all the cores, after one.
Okay, so everything that starts with OpenMP.
If everything is comparable, this is exactly this. I'm either running one job in parallel and making 64 jobs, one after one, or launching 64 jobs in sequential, but aside one to the other.
Okay, thank you. So
at the end, I produce the same amount of work.
Yes, syntactically, it's everything that starts with OpenMP is the vertical lines thing. And
OpenMP is on the right. Sorry, I should have written. This is this OpenMP.
What?
Because I'm using many cores on the machine for one single run. Here I'm using one core.
No, I mean on the histogram.
Yeah.
You call it OpenMP when it's multiple
when it's
jobs.
Multiple when I'm using multiple cores in one run. Here.
Oh, you call it sec when it's okay. Thank you.
OpenMP, this is I run 64 jobs but one after one taking all the machine. One other job which is taking all the machine, another one, and 64 times. Or I run 64 jobs in parallel, but all sequential. In the end, I produce exactly the same amount of work. Huh? This is just a different way to schedule it on the machine. User bin time. So if you're, Joseph, you're on which kind of operating system? There is a command to install it, but I forget which one. Ah, but you are in Podman. Did you pull the last image? Probably I made a mistake to avoid to, because I uploaded a new one yesterday. If you have an old one, probably you have the mistake. Ah, you get it if you make which. I don't know. Because here I have it. You take the which image, the VS Code one or the other one? Joseph. Joseph, otherwise you can edit the script. I'm calling myself. You can just remove the line to have the. So you will have an output a bit in a more friendly way. Where it is? Launch menu. In this script, if you search, there is a user bin time here. If you edit the script, you can remove this if you want. You will just lose part of the cleaning of the output, but you can still use it. Joseph, this is in a launch menu. Just remove this. Sorry, where I am. In the end of the file, when I'm generating the job parallel, you just remove slash user bin time, blah blah, this part. I will put paste. Are you convinced by the blocking? No, this is too difficult. No, clearly the pyramid, to be honest, the pyramid, this is clearly pushing the limit. But you have seen the gain, huh? 12. This is not nothing. But in production, in many codes, make the blocking just simple. Huh? One rectangle as a block, and make it in the L1 or the L2 to be seen where your program is efficient for. But clearly, this is a part you might want to implement in real life. Okay, the pyramid this was mostly to show you up to where we can go in practice. Sorry, I should have written in the text. I will put the line. Yeah, I was saying maybe I wanted to show you a bit the code. So if you go in SRC, lib, blocking, all the blocking part is implemented here. The basic blocking, which is relatively simple in quotes. And the data model. So the data model, I will just show you one thing, where it is, simulation, data model Gray Scott. Data model, this is more a class where I register all the variables I will have to compute when I give a size for a cache to compute the rectangle of the right size depending on the number of variables I will use. And because if I have 2 variables, I need to use half of the cache for each one. If I have four variables, I need to divide and to have 1/4 of the cache for each variable for a given cache size. So this is just a way for me to inform the way the blocking class how to split the rectangle, and I can show you an example. Here is just how to show what is the most interesting thing to show. Blocking constructor apply. No, this is in splitting. Data model. The data model permits when I give a given rectangle, I can give an aspect. And you remember the aspect I was saying? I want the rectangle to be more large than more wide than more high. I want also to keep some alignments. This I didn't tell you already, because of the vectorization. I don't want to break the vectorization, so I want to keep some alignments. And I included all the rules like this in one class, which is responsible of making the computation of the base rectangle for the cache. To have the right sizes which fit in the cache is has the right aspect in terms of wide versus height, and the right alignments. So again, this you can do by hand, playing with the indices directly. You will fail several times by making some mistakes, but you can succeed by making it automatically for the basic blocking. For the advanced one, you need to have more software engineering to get it. I stop here? Yeah, we stop here and we make a break for half an hour. Yeah. 16:10 or 16 o'clock? 16 o'clock? 20 minutes of break? 30? 30 minutes, so we start again at 16:10. 16:10? Okay. Nice for everyone. Thanks. prêt? Ready? Okay. Ready for everyone online? And we will go. Someone is writing, so I will wait. No, it's okay. So there was a question just before everyone left, which was blah, 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 about vectorization. Yeah. Is it possible to get both vectorization and blocking? Of course, yes. If you remember in my message, maybe I need to take the other presentation just to show again. Pyramid. Yes, of course you can get it, and you should get it, because if you do only the cache blocking, it's at some point a problem for the performance. You remember that I said here that I was making a part of my layer of my software which is handling the scheduling, how I schedule the blocks of my execution, and under the hood of that I have my kernel implementation. If you look in my code, you will find that there is some naive implementation, of course, not vectorized. There is the implementation of Pierre, which is fully vectorized and optimized and a bit faster than mine. And some unroll and unroll CPP version which are present, and kind of in the middle of the performance between the Pierre one and the naive one. So yes, of course, you can mix both. This is just that in your code, you need to think with layers. There is a layers which schedules the blocks, and inside you make some kernels which work on one block. Okay, and your kernel on one block should be vectorized. If you do that, you have both. Okay, so no problems. They are not. This is some problems which are not interacting too much one with the other, as long as you keep the alignment in the blocking size, to not break what the vectorization has done. I think it answers the question which was asked by Abdul. Sorry for the people online. Also, I made a mistake when I wrote the line. I was saying CMake build type, which was with an A in release instead of release. So take care if you think that the execution of my program is very slow. This is because there is a mistake in this character for the CMake command. There is two general questions. Is there a way to analyze software to easily locate this sort of stencil computation functions? To auto-detect that there is a stencil, no. This is up to you to know what you have done in your software. I mean, at least I don't know some software some profiler which automatically detect this. To detect that we are memory bound and we need to optimize our cache, I will show you during this presentation. Okay, so yes, there is some tools to look on that and to know that we need to optimize a bit our memory accesses. This is some expert tools, so sometimes there is some problem. So thanks, Joseph, for the question. So we move to the hot topic we will have now, which is the profiling. So profiling, I will again say a special thanks to Adrien Grassland, which was making this presentation last year, and I took back, I mean, the following of his slides to make mine this year. So thanks to him for the basement of the support. We have 2 hours, so I will probably not see everything, but if I can follow my path, I will go from some very simple tools, which you already know, so we will not pass a lot of time on them, to some more advanced tool to measure things in a program which is running. I'm a bit sorry for the last part at the end, the performance with perf. You will not be able to run it on the cluster here because, of course, this is the kind of tool the administrator tend to block for some security reason. So if you want to run this part of the execution after the 0.5, you will need to run on your laptop. I'm sorry about that, but most of the profiling tools which are making deeper things on the machine are not allowed on most of the servers for security reasons, because it permits to spy what is happening on the server. So in a first introduction to profiling. So the performance of a program is many things. not one, a lot. Computing, memory, weighting the OS, making the IOs. I simplify a bit, but already those four are four big problems. And you need to know at some point, estimate what are the limits of your system and where you are with your program on this limit. So for that, you need to make some measures and try to understand if you are close to the limit of your system, so you are already optimized, or if you have some gaps to improve a bit what you can do. I like to say that this is a bit like if you are a physicist, you have a world which is unknown, and you need to make some measurement on it and try to understand what is happening in this strange world you think you know. Either the hardware, the libraries you are using, or your own software, because sometimes you also forget what you are doing in your own software when it's becoming big. So as a physicist, you will need some tools, some probes, to observe what is happening in your program. So as a computer scientist, we will be just like physicists, measuring what is happening. Of course, at some point, you will need to compare what you measure with what you expect. So you need to have some knowledge on the architecture on which you are running on to know the limits of this machine. This is one of the difficult parts, because we most of the time don't know the limit of the machine in our head, and we need to search and try to understand if we are close to those limits. This is an experimental path. Profiling, you need to practice to understand well this way, to become fluent. It's not something we master from the beginning just by launching a tool. You have seen Macao. Well, Macao is a very difficult tool in practice. It's a tool done by experts, a bit for experts. We'll see now some tools which are a bit more simpler, but which one of them also which can go deeper and need some better understanding on what is happening behind to use it well. About perfect measurements. You think you are in a computer, so in a virtual world where we have a clock. At each tick, it's making one thing. One. Already many. We have seen the superscalar architecture, which is making many instructions at the same time. And you might think that at some point, because we are in a controlled environment, we can measure everything with the precision we want. We can say we handle totally the machine, so probably we can make a fully precise measure of anything. Totally wrong. This is not possible, because as soon as you will measure something, you will change the behavior of your machine on this thing, so change the measurement. So there is some limit depending on the way you will measure your program, on the precision you will be able to obtain about that measurement. And you will have to take care of that when you are interpreting the results you are looking on. Where to start from? Because there is plenty of axes in terms of performance, the memory, the vectorization, the pipelining, the IOs, and a lot of things. And you cannot start by spreading yourself on everything. So that's a problem with many dimensions. And at some points, on where to start, I will say your intuitions can be also a good helper. Your experience a bit more. So if you practiced a lot, you have some feelings on what can be wrong depending on the program and the way it behaves on the machine with some looks. But when you start from, try to look at the program on different aspects to try to understand where you think there is something which could be possibly wrong in terms of performance. There is anyway a good thing in this path. We can recall the Pareto principle, which is saying that 80% of the problem arise in practice in 20% of your code. This is very rare. It arises. That 100% of your program is spreading the same amount of time for every function. You most of the time some function which take more time than the others. And of course, this is where you need to focus to optimize your program. Okay. So the first point where when you are making some profiling is to search what we call the hotspots, the function which cost more than the others, and this is where you will make the tuning and the effort to optimize. The rest, you will probably consider that it's okay how it is. But for that, you need some tools to look at it. So we will start from a very high level. to look at the program in a very wide range. First with the time command, which you already know. I will not pass a lot of time on this. The time command, I like it for some things. Already it gives me the amount of time my program is taking, which I can compare to what I expect a bit, even if I need to guess what it should be. But there is something which are interesting. Here, for example, you see that time is giving you three numbers, the real execution time, so the time you passed in front of the machine to wait the program to finish. The user time, which means if you have 4 threads, you should have 4 times the real time in terms of execution of resource consumed in terms of CPU. So already, for example, in this run, I have a 1 minute run and a value of user, which is three times the execution in real on 4 cores, which means that already I lose a bit in terms of scalability. Just with a simple measurement, I already see that there is a performance problem here. And we have the system, which I like to look a lot. Me, I'm an operating system programmer, so me, it's system, this is my world. System, here it's 3 minutes. So for an execution, which is 2 minutes of CPU used in user land, I have 3 minutes passed in system land, which means that probably my application passes time to discuss with the operating system and call the operating system to exchange with him. Okay, so there is probably a problem in terms of performance in this code. You have probably noticed that there is a time command which is provided by bash, the shell 1, which is printing the thing that way. And you have the /user bin time, which is the same command, but not providing the same kind of outputs. But /user bin time, I like it. I prefer it a bit because I can give a format and format it as I want to get the values I expect. Yeah, there is more metrics also it can export. And I can get also the time in seconds, because when I want to make some plots, I don't know you, but this 1 minute, 12 seconds, I need to convert it to make it in my Excel, which is not very nice. Where with /user bin time, I can make my plotting, my comparison with different execution, just by copy pasting the value directly, because it's already in seconds with a comma. So me personally, I prefer to use /user bin time most of the time. This is the first command I'm using when I receive a program. I launch /user bin time just to compare with various parameters of my program, how it behave, and already get a view if this program is passing the time in threads, in operating system, or not. And how it reacts on the different parameters we have. I don't know if I make the demo now. I will probably skip the demo, this part of the demo. We'll do it after that. No, let's do it now. I will not pass a long time on this part because you know already time, but just to be sure that everyone is ready with the virtual machine, with the Docker containers. So if you take again the container we have just used for the past presentations, normally you still have it on your laptop. You will notice that in the example directory, there is a directory which is profiling. So for this part, profiling, you can also run it on your own laptop if you want. It's quite simple. It depends on nothing. With a README, with all the stages, we will have up to the perf presentation. So you can follow all the steps just by following the README if you want. Most of the things are there. I will just show you the program example I wanted to show before. So I came back to this directory for profiling. I will go to various tasks. So I made a program with many tasks, different tasks. So you can /tasks. So I have a single core task, many core with memory alloc. In practice, it's making a lot of mallocs and free in the middle of the loop. So calling the operating system, as I'm saying. There is a core with multi-core with critical. so mutex in the middle of the loop, core with I/O, and mini core optimized, so fully speeding on the CPU. So if ever you want to play, you can compare with /user bin time, many of them. We can try tasks single core. I can put in the container in the. So just you will see that with single core, normally you have exactly the same user time than the execution time. Huh? This is expected, of course. I need to give the path to the example. Maybe you can give a number at the end to reduce a bit the execution time if you want something shorter. 100 is fine. Normally, it's not too long. Yeah. So here, user 5 seconds. Well, normally it's okay. Not too much system, and elapsed 5 seconds also. So I have elapsed equal to user. I'm using 1 core. Okay. And system mostly nothing. So this code, we don't have to take care of the system. It's already quite well. I will just run the one with memory just to see the system example. This will be enough for this for now. No. Many core memory. Memory alloc. A bit slower because it's using the system and using many cores, and I am on a large machine, so I have a lot of cores. Maybe I stress the machine a bit too much. Let's say less threads, just too easy. Okay. Threads equal 4. Long. Why it's so long? Yeah, so here, 2 seconds of user, 20 seconds of system. Very slow on the system. Huh? I'm calling the system all the time, so this program has probably a problem. This is what I'm saying. I made a malloc inside an intensive loop. Okay, if you look at the code, you will see that there is a loop plus some malloc plus some computation, which is very short. So already with /user bin time, you can see some problems. Okay, I will not pass more time here because you already know these tools, and we will discuss more the rest. So at some point, sorry, there is a question on the track. To profile in an isolated environment without forcing core affinity. If you are on a system where there is many people running, of course, you have some difficulty. I would say binding on one core or on a few cores what you are running on is one of the best things. Of course, if you are on a shared system, you never know what you are measuring because the others are also using the system. Okay, so it's better to run this kind of thing on your own machine. So probably for the benchmarking, I will discuss during this presentation if you can work on your laptop. This is a bit simpler. But yeah, if you are on a shared system, you are never sure, at least for something like time, about what you are measuring. We'll see Valgrind, for example, don't have this problem because it's emulating the program. But for the measurement in terms of system-wide, this is a problem. The next step, look at your system in terms of your system as a whole. So here you probably know I will not pass a long time for this. You have edge stop. which probably you know. Who already use HTOP here? The half of the person here. BTOP, you already know. This one is less known. It's a bit more recent. KDE GNOME monitor, or the monitor you have on your operating systems, probably most of you know. And me, I like also to have, when I'm developing on my development laptop, on my development station, I most of the time use widgets, which I can have to plot my CPU usage all the time. So I just have to switch to look at when my program is running, where I am with the core usage, if I'm parallel enough or not. But this is more for helping me during the development to be faster. Some questions to ask when you are looking on the full system. Am I using all the cores efficiently? Is my memory full? Can arise also sometimes if I'm in the swap. I am doing a lot of IOs, and is the OS called a lot, the operating system called a lot. So to play, I will play again with this small executable tasks we have seen before. So with HTOP, I like many things. First, maybe I can show directly in the server what I like with HTOP. Maybe I need to open a new terminal, put it on top. Up. HTOP. HTOP, I will see many things. Let's take task. Many core with malloc. Let's say this one. No, single core first. Single core. Single core, I see my task is running here, 100%, so it's not moving too much. Ah, it has moved to, oh no, it has stopped. It is too short. I need to run it longer. Let's make a longer run, 10,000 repeats. So it's running on one core. So depending if you're running on a laptop, most of the time you will see that it will move from one core to another. Pierre has already explained that to you. That to keep the frequency high by controlling the temperature of the CPU, it is moving your executable from one core to another. Here I'm on a server. A server has more ventilation and more way to cool down the CPU, so it has not, I mean, when I'm using only one core, it has not some requirement to move it from one core to another. So it tends to let it on the given core. But you need to think that if your application is moving from one core to another, each time it flushes the caches. So every time it moves, the caches are flushed. So you need to load again the caches because you are on another core. So this can be something which slows down your application. If your application is dependent on the caches, the movement of the application can be a problem. For myself, I'm on a dedicated server because I wanted to be sure to not be perturbed. Sorry. For you, you have to account with a shared machine. For the question from, sorry, it was Stevenson. I can run the other one, which is many core. I should have called it OpenMP, so it's usually simple. Many core memory alloc. Here I will see something interesting. OMP numfred. Yeah, let's use the full machine. Here I'm seeing that all my cores are red, because HTOP prints in green the CPU computation and in red the operating system. So with HTOP, I like this a lot. When I'm launching a program for the first time, I all the time do HTOP on it. If I'm passing all my time in my system, I know I need to look on the system part of the performance. If it's all in green, I need to know that I know that I'm all on my CPU side on computation, and I need to look inside my program to optimize the things. It's already one of the nice information. What was the question? So for this benchmarking, you can do it on your laptop. I don't need a big cluster for the measurement I need now. So you can fetch the image on your laptop if you prefer to be sure you are alone to test this. Also, maybe you can make the perf part if you are alone on your laptop. So this is htop. So htop, me, I like it just to get the view. Is it on the system? Is it swapping also because I get the memory? Sorry, I should have shown. You get the memory part, if it's filled or not. My memory is full or not. How much memory I'm using, I get a view. And when I have a program I receive, I don't know, I need to get some idea where I am. Me as someone who optimizes codes from other people. So htop is already a first look, which is very nice. btop. btop, I like it a lot also for different reasons. It's not showing the same things. Me, what I'm liking a lot is that it's showing is a timeline. It's plotting the usage of the CPU over time. So I can see if there is some bump. Sometimes I'm using system, sometimes user. If the cores are fully used all the time, or if there is some holes, the program slows down at some points and not using all the cores, then accelerate again, etc. I have the temperature of the cores also. I am making the CPU very hot. And I can get the I/O bandwidth also. You get some plots about the I/O. And if you are using a GPU now since a few years, they included also the plot of the GPU usage. So you get a view, is it using a GPU, is it using the CPU, how much? For a first look, this is already a lot of information to get about a program you don't know. btop, maybe I can make the demo just to be sure. So instead of htop, I launch btop. Here I will launch many core directly. I zoom too much. Yeah, btop as a default is that you cannot launch it if you zoom too much. So here I'm using the full server all the time, so I'm quite happy. And I see the plot which is arriving here. So I will not lose too much time here because this is some tools you already know, and it's not where your expertise will bright. Sometimes you want to get logs about the performance of your application. So you want to get exactly the same kind of tools than htop and btop, but by being able to log the output in a file, so you can make some plots which you can reuse in a presentation, in a paper eventually. So you can use the cstat package with the SAR command, SAR, which is printing the CPU usage. So I can show you line by line. So this is exactly the same thing as top, but in a way you can dump in a terminal. So SAR, you need to give the number of seconds you want to wait before each printing. And for every second, it will print the usage of your CPU, and I/O system on the system. The good point is that you can pipe this in a file and get it as an output to make some analysis post-mortem. This is interesting also on a server when you're running on a job which is remote, where you cannot connect on the server to make htop or etc. In practice, SAR has also some options where you can get a lot of metrics. If you type -a, so this is a bit too much in my terminal because I have a lot of cores. You can get a lot of metrics in practice in this. So you can look on the options. I will not dig on all of them. You can get the network to survey all the network cards, all the hard drives. If you want to look at a specific hard drive, you can get some metric on this one. You can select by options. You can get, what else? Page in, page out for the swap. A bit too much data for this server because I have too many cores. The numbers for every course. And where I am. Bref, a lot of data. I will not get in all. You can get also for each CPU the usage every second to get the stats for every core to get how to see how your processor process moved to one core to another. So a lot of things you can get by SAR. You can get, of course, by --help. Sorry, I'm in uppercase. You can get, you see all these metrics about networks, power management, moon points, I/O system, paging system, etc. So this is one tool which is efficient to analyze the things at the system level, again, when I'm not running a single program. So again, I will not lose all my time here because it's not the most interesting tool. You have another one which is exactly the equivalent, which is dstat, making exactly the same thing but presented in another way, with some colors, etc. So this is something Adrien was presenting. Myself, I was not too much using those tools every day, sometimes only. Let's say dstat. So dstat, you see exactly same kind of presentation than before, and I can pipe it to a file to get the log. So here I see that I'm using 100%. I'm making a bit of IOs, not too much, on the system, etc. About time, I'm thinking there was one person also speaking about hyperfine during the question for Pierre. Hyperfine is also a very nice tool to make some performance measurements. So it's repeating the execution many times and computing the error bars for you about the stability of the run you have made. I didn't present it here, but this is also one nice tool to use for performance analysis. So now we have looked at the system level, okay? But of course, we have a single program most of the time to optimize. We know exactly what we are running, and we want to look in. So we'll zoom a bit, take a photography in macro to search for the performance bug inside our program. So for this, the first point is I want to search the hotspot where I pass my time in my program. If you have a program like Grayscode, it's quite easy to guess from where my cost will come, because I know the function which is costly, there is roughly one. But if I'm in a program with, I don't know, I was working with 1.5 million lines of C++ at some point, of course, you never remember what you have done in this program and which function is costing a lot in a real life. So not to guess what you need to optimize, but to get some proof and to measure, you need some profilers. So there is many ways to do that. A first one is to inject some probes into your program. This is exactly what it's doing. So you can do it by hand. Put some measurements or time measurement in your program directly. This is what I did, for example, for my implementation of Grayscode. In HPCs, it's quite common to do that by hand because when you are on a cluster, you sometimes don't have the tools you want to use to profile. So have this done by hand is quite fine, even if you do it at a low granularity in general, because you don't want to put a probe in every line. Okay, you put it on some hot functions. You already estimate that they are probably the hot topics of your program. There is one which is very nice with GCT or some other compilers, is gprofiler, which is a GCC plugin which at compile time will inject at every entry point and exit point of a function a marker where the library at the execution time can measure, I enter in the function, I exit the function, and rebuilding all the call tree with the cost of every function. So we can use it now. So I'm going there. So I will change my program. I will move again to the Grayscode simulation now to get something more interesting to look at than a single loop program. So I go in free Grayscode CPP as for the previous presentation. I will put in the Discord just after that. Build gprof. I'm building for gprof explicitly, so I create another build directory for this because I will have a special version instrumented. So now I do cmake -d cmake build type equal release -d cmake cxx flags equal -pg, pg or gp, I always forget. PG. -d CMake C flags. No, link flags. CX6 link flags. That's it. I will paste it in the command so everyone have it. Huh? Sorry. Equal PG dash PG, and I forget the dot dot. Okay, so I will cd tilt slash noise cut cpp. I will paste in the terminal in the Discord, so everyone has the command. And there was one question I seen. I mean, not the purposes only for benchmarking. I mean. This you can do also if for the people who have Slurm, you can also just use an srun command to launch a job on a single node. I mean, on a node you are single. But for the lab I'm doing, if you can do it on your laptop, you are sure that you are alone. Huh? This is probably a better way to do it. No, this is the command I wanted to take is there. Where I am. I'm lost. mkdir build gprof. And I will paste this line not to make the mistake I made before. It is there. CMake. Copy. And paste. Copy, paste, copy, paste. Make. Okay, so I pasted the compile, so I compiled. I will compile in parallel to go faster. So now I have a program which is instrumented. Huh? In every function, at the entry point and at the exit point, there is a measurement which is introduced. So I run. So normally it produced, no, what I did. I don't have the output. What I no gprof run, sorry. All the time forgetting this. I made a mistake, of course. -pg, -pg, what I did. You'll see that making a presentation of profiling tools is a problem because we change those tools every 2 seconds. Maybe this is because I run it in debug mode, in non-debug mode before. Gprof. No such file of directory. What I did. No, but I get the output. It was just sorry. So you run. Sorry, you make a first you execute your program. So sorry, I will come back to the release version, not to use the non-optimized one. So the command I pasted in the Discord. You run. It produced a profile file which is in your directory, which is gmon.out. Sorry, I forget. and you say gprof dot slash your executable to get the profile output. So you get in your terminal the summary of the execution. So here, with no surprise, we get that the kernel unroll sec is taking 90% of the execution time. Okay, so you get the hotspot of your program. This is trivial in Grace code because we know by advance that it will be the kernel which is taking all the time. But if you have a large program, you can find where are the hotspots in your execution. So I will put in the ./run and gprof./run. So first way to get a measurement, but there is a small problem with that. No, not here. If you look the execution time, sorry, I should put time before. Three seconds. I will probably not see it on this machine. Three seconds. I have mostly the same execution time, but I have changed the program itself because I have put some probes. So here I don't have a larger execution. My program is running quite at the same speed, except if it's in debug mode. Because if you run it in debug mode, you will break all the inlining. The only thing is that I changed some behavior of the program because I put some probes inside the program, so I changed the programs. Okay, it's not behaving exactly the same way than before. So this is quite interesting to get the hotspots, but not too much more. And also, have you seen some other functions? If I'm making the rendering, for example, I'm using for the rendering, let's say I create the images directory and I use run --render to produce the images. I'm using libImageMagick to make the rendering. So I'm calling a library which is making the rendering for me. And if I gprof this, do you see the library here? libMagick? No. Because gprof is seeing only what I recompiled. The library from the system, I didn't recompile it. Okay? So I see only the part of the program I recompiled with the gprof instrumentation. So it is quite nice if I'm looking only what I'm doing, but if I have a big part of the time which is passed in a library from the system, I will not see it. Okay? So this is one of the limits of gprof. It's showing you only your part of the program, not the rest. So there is another way to do that. We can do emulation. This I will skip, sorry. Where I am, emulation. Emulation, instead of instrumenting the program, so needed to recompile it by putting some probes explicitly inside, we can make an emulation of the program, so having another program which takes the first one we want to execute, which reads the instruction and emulates the instruction, counting the time it takes, executing the next instruction, counting the time it takes, etc. This kind of emulator is exactly what we call Valgrind. Valgrind is an emulator made for performance analysis because it will count the time you pass on every instruction, for example. This is one of its capability. It's also used for memory checking. But one of this capability with two tools, which is provided by Valgrind, is call grind to make the measurement of which function costs how much, and cache grind, which is capable of measuring the cache usage of your program by emulating the cache. So to run this, we need just to recompile our program again, but this time in release with debug symbols to have -O3 with -G for the debug symbols, and to run valgrind --tool. Sorry, this is -- here. dash tool equal call grind, and my program to run to see what I want to observe. One thing, Valgrind is not supporting parallelism. I mean supporting. It's supported, but it makes the threads running one after the other. Okay? So you will lose the parallelism, so it's efficient to analyze a sequential program in practice. So we will currently focus ourselves on the sec part of the Gray Scott implementation. So let's run call grind. This I should have done in my machine because call grind came with a graphical interface, which of course is running only local. So I will run it locally. So I will run again. I will show how to observe anyway the result on a remote server, but you will lose part of what is interesting in the tool. Build, release, debug. So I need to -cmake build type equal release with rel with deb info. Boom. And here I see that I have -g, -o3. So I'm optimized, but with the debug symbols. Now this is what I want. Maybe I can paste in the following. I have only 7 rows in my gprof. No, there was no new CMake command. The one I give was a good one. 7 rows. What you mean, Joseph, by sorry, I will come back to gprof to answer the questions. You mean compared to what I have in my slides? 1, 2, 3, 4, 5, 6, 7. This is exactly what you get, no? Sorry, some people are answering, so I will just continue and come back to the question after that. So I build, so I'll do valgrind -- call grind / my program. I will run sec because it's not interesting for me to run the parallel version for this. -- tool equal call grind. This I can give for valgrind for the people. This is what I wanted to do. So we notice that valgrind is quite slow in practice. We see that here the number of cycles is 91. So it's roughly 100 times slower than the standard execution. Of course, because it's making emulation. It reads one instruction and execute many instructions to emulate what it is done by one. So this is a tool which is slower. So maybe I can reduce the number of time. Stop, please. I will say -s. 2000, it will be enough. Let me correct it in the just 2000. So there is an interesting question from Stevenson. In case we use a call grind, what if threads share data and control dependencies? Yes, valgrind is not handling that in that way. So if you have a parallel program, valgrind is not the right tool to make the performance analysis because it will create some false negative, as you say. So there is some other tools we will show just after that, which are capable of handling the parallelism. But Valgrind is a nice one, so I wanted to present it. What about using a larger font size for typing along? Ah, yeah, true. Okay, now. I said to the others to grow the typing, and I didn't make it myself. No. Yeah, thanks. This is because this terminal, sorry. So I executed valgrind --tool equal callgrind, run the sequential version, and a short run, not to have be a long execution. And so this you cannot do in the container. So here I will give you a command to be able to get a call graph annotated in the container after that. Normally, you take the call grind, it has produced a call grind .out with the PID. So I do kcache grind call grind up. And so sorry, here I will not be able to zoom. This is the problem also of this kind of tool. So here you get directly the list of functions with the cost of every function, and the annotated call tree, which is where it is. So you have here the carte des fonctions appelées, the map of the called functions. So here 99% of the time is passed by in sec in my kernel, which is seen here also because you have Grayscott unroll sec, which is taking in terms of inclusive time, the total time of execution 99%, but also in exclusive, in proper time, 99% of the time is passed here. So I know my hotspot is in this function and I need to look at it. You can also get the call graph. So you can dig directly in the call graph to see what this function is calling. So this function is calling nothing, so I don't see it. Here there is a question. Can Valgrind emulate an architecture different than the one it is running on? I don't know. Probably not. I don't know. I think if it's compiled for x86, I think it's run for x86, but I'm not sure. The problem is that Valgrind is not, it's loading the libraries from the system. So at some point, if you don't have the libraries for the system, for the architecture you want to emulate, it will not be able to run. Thanks, Joseph, for the question. You can get some code source annotation also. Where is the line? Here, the line which costs the most is here, with 80% of the time on this line. So I can get directly which line is costing in terms of instruction and cycles for the emulator. So this is the line I should optimize if I have some optimization to do. Okay. So this is not a perfect tool. Also, it emulates. So this is not exactly producing exactly what is happening on the real processor, because it's an emulator. The processor is doing some other stuff, probably in a more complex way. So this is giving you a kind of relative view on what is happening in real life. But for a first look in a code, this is quite fine to get it. Would you share the history of your shell, probably? Yeah, the history of my shell you want. So, first thing I made. No, I have it here in the slides. Valgrind. I'm on Valgrind. Emulate here. I have it here. So to run, you need to build your program for Valgrind. So meaning with debug symbols and in O3, optimized with debug symbols. Then I do make, and then I run valgrind --tool equal callgrind /run, getting a smaller problem and the optimized version I want to check. What I was saying is the overhead, which is quite important here. There is a question here.
The question is about the emulation of cold grained. It's based on what? On sampling some workload on the architecture, and it's an interpolation of all the workload, or?
So it's counting in terms of instruction. It's counting in terms of instruction. For the cycles, it's a kind of estimation of what should be the cycles on a real machine. But it's not the exact cycles which you will have on an Intel processor or on an AMD. It's a kind of simplified machine which is taken in account in the simulator. So you have some cost for different operations, different instructions, which are what they are, not the real one from a real architecture. And for the caches, they emulate the caches with a very simple model. So this is a model what they provide, not a real-life architecture. So this gives a first hint to get the hotspot, to see where the costs are, but not to get the real cost on the real machine. We will see later another tool which permits that. But already this is working quite well. Also, Valgrind is running in any machine. If you are on a cluster without any administrative rights, you can run Valgrind on an HPC center or anything. So this is a nice tool for that. Yeah, history, but I can do the history. Sorry. But I didn't make it here, so I need to make it here if you want. I will print the history. Make -16. -tool equal grind /run-o sec -s print run. Okay, I will not execute up to the end. You wanted what you wanted is what you wanted remotely? I have seen the question. Yeah, the problem is that I changed the machine because I want to run locally, so I cannot do that for this. But I will take care to do that for the next part, sorry. Maybe I can share this part of the... Done. The slides are on. The slides are. If you want the slides, they are for the commands. They are also in the Gray Scott calendar. So yeah, cache grind, call grind. Sorry. So call grind. So it permits you to see the spots. You can put some option to get some deeper analysis with the assembly language. Also, if you want the assembly. For example, if you put some options, you can get the loop back. If you go in the view of when you open the view, it tells you which option to add to the run to get this kind of annotations. So you can detect the loops, etc., and everything. What I wanted to present to you now is sorry, I didn't make the command line here. I should have. You can, if you're on the container, you can use gprof to dots, which is generating a gprof image. Gprof to dots. I don't have it here, so I need to go in my terminal. I should have let it go to the end. So for those who are in the containers, you can use gprof to dots, which is a kind of simple viewer, generating the call graph annotated in in the shell. I mean the shell, in an SVG, in an image. Why it's so long? Val grind, call grind. Kcache grind is something you need to run local because it's using the X11 protocol to display. So you cannot use it from the container. Sorry. So I will show for the people remote on the container. You are able to use it via if it's running. Why it's so slow? Because I forget rel with deb info. What I did. Far slower. This is the point of Valgrind. Huh? It's increasing a lot the execution time. Come on. Why it's so slow? I have something running in the back. Why it's so slow? No, I'm not rendering. Well, let it run. Frankly, Valgrind, I prefer to use it with the graphical interface. Huh? The call graph, I can show you how to generate, what it generates. I have one. No, I don't have one here. I should have put an image here. I think I made it. Let me obtain my. I will do it locally. Profiling, readme, gprof2. No, gprof2 call grind. Yeah. Up. I will make it locally. It will be faster. I don't know why the server is not responding. I already have my call grind here. So I just do gprof2 callgrind.pid. So I'm calling gprof2 format callgrind because it's a tool capable of formatting the output of many profilers. Pipe, I pipe to .-tpng to callgrind.png. And of course, I don't have it here, so I need to download it. And I think I put the link. I should have prepared this in a different way. Demo effect. This is done here. Set. Okay. So normally I have it here. CPP, build release, and I have my callgraph.png. And you have a call graph like this, which is generated. I can zoom with the annotations and the colors. Oh, the colors are pretty not too much readable, I found. You can play with some options to change the colors, but in red you have the hot path, and in blue the path which costs less. Okay. Personally, I prefer to use Kcache grind to dig in the profiles. It's far more efficient than using this. This you can use the gprof to dot. You can use it remotely when you are on a remote cluster without any graphical interface. I put the command here if you want to use it. So I will not pass more time on this. What is more interesting with Valgrind, and frankly the real reason I'm using it sometimes, is more Kcache grind. Cache grind, sorry, which is a cache emulator to validate what we have seen before. which is a way to measure. So we can use dash tool equal cache grind. So it will simulate the caches of our CPU this time and give you some numbers about the way it is running. So I can make the simulation myself here. Cache grind, dash cache sim equal yes, dash branch sim if you want another branch simulator. There is 2 simulators inside this tool. So same thing, it will produce you an output to open in cache grind, same way, and print some summary at the end of the execution also. Of course, cache grind is a bit slower because it evaluates the caches, etc. So it costs a bit more the simulation. So the overhead is a bit higher than call grind. And you see that the execution is quite slow. And here I have a summary of my L1 execution, the misses, the rates, etc. Same thing for the L2, L1, L2, and L3, last level cache. L1 and L2 because cache grind, sorry, is emitting only 2 levels of cache, not 3. Okay, there is an L1 and an L2, point. So you get some numbers, and if you want to compare, for example, for the, I will not do it now to not lose time. If you want to compare the L3 pyramid with L1 blocking with the sequential version, we can see here that the sequential version has far more cache misses in the L1 than the pyramid one. Okay, so we can see with this tool that we effectively made a cache optimization with our application. Okay. I will stop here for this part. I stay 30 quarter. Yeah, I will stop here for this part. Yeah, as I said, this is not because you reduce the cache misses that you gain in terms of performance. Huh? If your performance is not limited by the cache, here it's a program I'm running in the cache as we are seeing before. On my laptop, I was not gaining by using the cache optimization because everything was fitting in my cache already. So it's not because the misses has reduced that I will win in terms of performance. So take care with this kind of measurement of cache misses, etc. This is not because I improve it that I improve the time in terms of execution. I'm improving the time only if it's a large number, which is costing a lot. Question here?
This is sort of, I mean, not strictly related to exactly what you're talking about, but CPUs, of course, have a routine for when to push things into cache and so on.
Yeah.
Previously, they've been very simple, but I mean, modern ones are quite complex.
Yeah.
Do you have any idea of how they have evolved over the last years?
The cache on the CPUs or the model of Valgrind?
Yeah, how to when they retain, when they switch out new bits of memory in the cache.
So in practice, the caches today are very complex. We will discuss that more in details Friday about how the caches is choosing what it evicts or not. We will discuss the algorithms. I mean, the simple version of the algorithm which is in. But now today's Intel and AMD also has very complex algorithms which are closed. We don't know exactly what they are doing. We just have some kind of idea when they do. This is why all the emulators about cache simulations have some problems because they don't know exactly what model to take to really simulate what is happening in the caches. Intel has a cache simulator which is very efficient and close to what they have in their real architecture in the amplifier and VTune simulator. There they have the real model because they know what they do, but with a model which is closed source, so we don't know exactly what they are doing. But the cache now is a very complex mechanism. Huh? This is a very complex machinery inside. So we said we had an emulator with a very high cost, not parallel, etc. So it's a bit a problem to emulate the program also. And we are not also in the real context of the CPU because we have a model of the CPU and not the real one. So the question is, can we let the processor itself counting for me what is happening inside? This is the question. There is a question about the reducing. I will stop here. Why, if we reduce the cache misses, the execution time will not reduce in your example? Yes, it will not reduce because the cache is there to balance the fact that the RAM is slow. But the RAM is relatively fast. So if you don't stress too much the RAM, it's fast enough to feed your core. This is what I was saying in sequential. I'm not saturating the RAM bandwidth. So I'm fast enough. I don't need the caches. So I will have some misses, but they will not slow down too much because the prefetcher of the CPU will prefetch in advance the data in the CPU fast enough. The problem will be that in parallel, we will stress the machine a bit more. And in this case, the misses will start to penalize the application. So there is a limited number of misses which are acceptable by the processor. After a certain amount of misses, it will start to penalize the application. So don't look the numbers in absolute value, but compare to what is acceptable for the machine. Thanks, Jacques, for the question. I hope I answered. Again, we will discuss a bit more this cache fetching, prefetcher, etc. on Friday by entering in details about the memory. So we'll dream. We can dream a bit. We are computer scientists. We like to dream to have something, and we finish to have it. We can dream to have some probes directly inside the processor to measure what is happening in the cache, in the instruction set, etc. And this is exactly what are the hardware counters. There is some hardware counter directly in your processor, which is built by Intel and AMD, to look at directly what is happening inside. This is what we call the PMU, Performance Monitoring, units, which can probe many things: the instructions, the flops, the scheduler, the prefetcher, the stall, the cache misses, retries, and everything which is happening in the processor is counted by some counters. So from this, we say, we are happy. We have a very nice way to measure everything. But, there is a big but. They are not built for developers. Those counters, Intel, as for AMD, they made those counters for them to validate that the processor is running the right way. Because if you make a processor, you need to check that everything is happening correctly inside when it's complex. So it's a bit the unit test of the CPU they use to validate that everything is running as they expect. So they are not done for the developers, so they are think in a way which is not very efficient for us in practice. For example, I speak about the speculative execution. If you count what is happening in the speculative execution, which is something which is cancelled in practice, you will get a wrong number of misses. So for a developer, you should ignore normally those numbers, but you have them counted in the pipeline of the CPU because I check everything. So it's kind of not done really for us. Also, as it's not done for us, there is no common norm to do it. So each processor has its own set of hardware counters. For every generation, they change each one. There is never two CPU versions where you have the same counters available. So up to you to update every time to understand what they make with the new counters or not. So the meaning is changing also sometimes also for some counters, again, because it is not done for the developers, but for the hardware builders. And most of the time also, these hardware counters, they are disabled for security reasons on clusters, because it permits to spy everything which is happening on the CPU, which means spying the processes which are running aside you, which is probably the processes from another user. Okay. So this is something you most of the time can use only on the developer machine, on your laptop, or on your workstation to make your analysis. There is also another problem. You can say I have an hardware counter, so it's running at the speed of the CPU, 3 GHz. Yes and no, because it's very precise to measure everything, but you cannot read the counter at the frequency of 3 GHz, because otherwise your CPU will do anything else than just managing the counters. So in practice, we are doing something which is sampling. We will not get a notification every time the counter is increased, but every 1,000 times, for example. So for this, I have a small demo about sampling. You have it in the sources I provided if you want. If I go in labs, profiling, sampling simulator, this is a web page. So I will repeat this loop 1,000 times. I will count every 500 events to increment the counter, and I will have a scaling factor of 1,000, and I will execute. So here I have the sampling count I have. As I'm incrementing I'm notified every 1,333 increment of the counter that the counter has increased. I will not be notified for a long time. And if I go a bit faster, sometimes I will be notified on one line, interrupted, and say, come on, get it. I will get an increment. This line has get all the price of all the others. Okay? Because when I reached this line, I was interrupted because the counter reached the max value, which is low, the threshold. Okay? And I assigned all the cost which has been executed to this line. So if I execute fast enough, long enough in terms of statistics, I will get the distribution of the price on the function which costs the most. But if I don't execute enough, I will have a bias because some of the lines will get more counters than the others. Okay, this is what we call sampling. So if I execute a long time, we see that it's popping up. I now see that all the for loops are getting roughly the cost it really has. But I need to execute a very long time to get the right count value. Yeah? Question in the back?
Yes. How do you actually know which line is being executed for the counters?
So when the counter reaches its threshold, okay, it's incrementing every time. Here, this is an instruction count I'm using, or cycles. Every time I increase the cycles, the counter increases in the CPU. And once the counter reaches the limit value, the threshold, it interrupts the program and says where the program is. Program is here. So I attached all the costs I have seen to this line, which is not exactly true because the other lines has also increased this counter. But I suppose that all the cost is statistically done by this line. And if I do it oftenly, long enough, statistically, the cost will fall on every line which has the high price. Okay, and I get something balanced. You see here that I get something relatively balanced after a long time. But I need a long number of execution compared to a single shot. I can play a bit with a smart example also. Here, if I'm putting 15, I will execute fast. 15, this is? Yeah, no? Yeah, 15. There is an interesting thing which arises here. You see the mistake? Someone here? Yeah, there is a kind of resonance, and the counter fall all the time, finish all the time to reach its threshold on the same line. Of course, this is not this line which is costing a lot. It's just that the sampling thing is making us biased in terms of what it is showing. Yeah?
Yeah, so does this mean we need a prime number for the sampling?
So ideally, the counters are configured in most tools to use prime number to not fall in multiples. But when you are using hardware counter, you need to take care of two things. First, you need to execute a long time to have a real statistics. So not executing 2 seconds, it's not enough in, with hardware counters. You get a precise view of what is happening, but over a long time in terms of statistics. And you need to take care of the interpretation of what you are showing, what it is showing, because sometimes it can fall down on the wrong line. Generally, it's not at the other side of the code, but it can be the line side, which really has the cost. So take care when you interpret the result of the hardware counter. It's not exactly what it is showing, depending on what happened in your program. If you execute not long enough. Okay, we stop the simulation here. We understand the limits of the hardware counters. So anyway, this is anyway an interest. So you have here the different examples I wanted to show. Also, there is one limitation. I say there is many counters on the CPUs for the cache misses, for the instruction, for the floats, for blah blah. But in practice, most of the CPU today, they cannot count many counters at the same time. Most of the time, it is 3, 4. And if you want to use more than 4 counters at the same time, you need to multiplex to say, I measure sometimes with two counters, stop the counters, start some others, measure a bit those counters, and multiplex like this by switching the counter over the execution. Okay. So most of the time we try to focus on a limited number of counters with the hardware counter and not to mix up too many counters at the same time. So it's not too much a tool to say, I will look on all the counters and see the one which is showing a strange thing. I will mostly use the hardware counter by, I know I want to look on that thing, and I will look on this counter about that thing. So this is already interesting when you already know a bit what you are searching in practice. So how to use the hardware counters? 2 ways. Either use the perf command. Perf is one of the commands on Linux to use the counters, or you use the CPU provider tools. Intel has vTune to use the counters, and AMD has also some, which I never use myself, so I will not present them. So perf is interesting because it's generic. It's running on every architecture, ARM, Intel, AMD, independently. Frankly, its interface is not very friendly, you will see. I will show you the example. Of course, it's not available on most clusters because it's using the hardware counters and permit to look at everything which is happening on the machine, which your administrator don't want in terms of security. So for this part of the demo, you need to work on your laptop. Sorry, I cannot. I mean, you will not be able to run this on any cluster. The default counter when you launch a perf is the cycles. So it's permit to get the hotspot, getting the equivalent of Valgrind and gprof. One thing, if you want to run on your laptop, you need to allow in your kernel for the full machine in terms of administrative stuff to allow perf to analyze the machine, to say which write it has, because by default it's disabled on all the sessions, again for security reasons. So you need to go to SU and to get this command on your machine. You have several values. You can allow it for almost all users. So you can disallow it for anyone. You can allow it to see what is happening inside the operating system or not, or allow it to use some ftrace, which is looking at all the processes running on the machine or not. So you can select a bit the range of things it can look at. So myself, most of the time, I say -1, so look at everything. This I will skip. So to use it, first way, to use it at the machine level. So for the full machine with perf top. So I use it exactly like htop or btop. I will run it here. So I'm on this machine here. So sorry, this part maybe don't try to follow yourself on except if you do on your machine, because on any others you will be limited. ./run. There is a question. We aren't able to perf. So perf, I'm using it on this is like the Intel tools. When you have hardware counters, you need to use your own developer station because you need to allow everything. Sorry for that, Stevenson. So I'm saying perf top. So it's starting to instrument everything. For now, I'm using nothing on the machine, so I'm seeing only the kernel functions because there is a K here. And if I'm running my program, maybe I should use a long one, 32,000. If I'm running my program, I see to start to see some options. Dash OMP, this will be simpler. Yeah, sorry, I was just seeing it. So here I see my run, the kernel, the function which is the hotspot. My run is too short on this big machine. So here I'm looking on all the system, and it is telling me which program is taking all the time and which function is this program. Okay, so I directly know that Grayscott kernel unroll OMP is the function which is taking all the time. So I can go in it, I can look on all the function of this program directly. Sorry, I can show slower. I can select with the arrows which line I want to select, press Enter, zoom in the DSO, so the executable which is responsible of this line, and I see all the functions of this program which have been seen by the sampling. So not the small functions, they will pass under the radar. And I see that 74% of the time is passed in kernel unroll OMP in this case. And I can click on Enter, annotate the source code, and I get the assembly language annotated. And I can press, this is S uppercase or S, I forget, to get normally the annotations of the sources. No, this is what? I always forget which one it is. Sources. Toggle to sources S. Why it's not going to? Yeah, okay. So here I have also the annotation on the lines directly, the cost on every line, where it's costing a lot. So I can focus directly on which line it is taking most of the time with sampling. So take care of what it is doing, but I can get directly the hotspot with H. And the hotspot is here. This is this line, the same than Valgrind was saying. Okay. So from this, I can get directly the line which is costing a lot. This is already quite a great important thing when you want to optimize your program. I will stop here for that. So here I launch currently perf. I launch perf for the whole system, which is not what you want to do most of the time because you want to analyze one program, not the system fully. This is exactly what I made in the demo. So there is a way to record what is happening on the machine, on the program. So I do perf. No, not here. This I can do with the terminal simply. I will do perf record dot slash. I will take again my run, not too long. Perf record dot slash run dash S3000 in OpenMP. A bit too short. Remember, if you have a run of 3 seconds with perf, this is not good. You need to really use a longer execution. So it's recording everything, and it will dump in a profile, and I will be able to browse this profile like with perfstop directly in the terminal. Perf report this time. So if you look, it has created a perf.dat file. here, which is the performance file, and I can perf report, which take a bit of time, to analyze my profile like before. Okay, so there I can post-mortem analyze exactly what I want. So here I'm at the hotspot, and the hotspot is this diffusion rate multiplied by full U, UVV, etc. function computation. So this is an efficient way to find the hotspot. Okay. So currently I use cycles, so the times and not the other counters. I will not play too much with perf a long time because if you want to look on all the counters which are available in perf, you can do perf list and then attach yourself to your chair. Perf list, this is all the list of counters which are available in perf. Find the good one, which is what is interesting for you. Okay, so there is some virtual one which are provided for you. I mean, not the real hardware one, but some simple one. You can look directly on this first list here, because the bottom list is a deep, very deep, the very deep part. But clearly, when you enter, except with cycles, I think perf is a tool for experts. When you know a bit what you are searching, you know this counter will permit you, when you know that you are making some mistake with caches, for example, with the L2 caches, and you want to prove your program is clearly having this problem, you target this counter which counts you everything which is happening in the L2 cache, and you look at it. If you expect to find something looking blindly in the application without knowing where you go with the counter, with the hardware counters, you will be lost, at least with perf. Yeah?
So how does it work with this keeps counters of L2 cache or L1 cache?
Yeah.
Because I thought caches was like it's only visible from the CPU side, like it's sort of an opaque object from the kernel, but that does not seem to be the case, right?
So the counter is directly hard-coded in the hardware. Huh? So this is the CPU itself which is counting and notifying the kernel sometimes. So the counters are really true in what they say, because they say exactly what has happened in the CPU. Not increment per increment, because I get it for most of the time. This is roughly 1,000. This is roughly 100,000 something the threshold they are using. Huh? So this is not the threshold is very high in practice because of the frequency of the CPU. Huh? You cannot read the counters every nanoseconds. Huh? This is not possible. Otherwise, the CPU will make anything else than analyzing your process. So, for example, for the L2 lines, you can get here the number of L2 lines you are accessing in your CPU. You can get the number of requests it has, the number of misses, and everything. But then you need to understand a bit your processor to know what counter is interesting. Myself, during my PhD, I was using it a bit, this tool for making things, but I was looking at the documentation to find the counter which is interesting for me, and then looking for this counter for this precise case I wanted to analyze. So this is a bit the limit with the hardware counter, except for the counter cycles or the virtual counters. If you look on this list, there is also some counters which are virtual, I mean software counter. I will find some. Sorry, the list is not printed in a very nice way. And I don't have them here. There is also some counters about what is happening in the kernel. Okay, not hardware counter, but kernel counters. Those ones are a bit more easy to understand and to interpret. Trace point events. For example, you can have some measurement about the power of the cores, the network cards, the blocks, which blocks you are using in terms of IOs. This is some hooks in the kernel this time, so not in the CPU. So you can look also with perf what is happening in the operating system directly. In practice, perf has been developed by the developers of Linux to optimize Linux, the kernel itself. So again, this is a tool for experts. So, yeah, don't be afraid with the long list of counters. Yeah, one way, if you want to export your counters, you can also generate, convert the performance data from perf to export it to the Firefox profiler, which is a viewer in Firefox, where you can get. I will not make the demo now, but you can dig in the profile over time directly by selecting the timeline if you want, all the calls, and having all the results over the counters, over the call stacks. This is another way to dig in the profile, same than in the terminal, but in your browser. Micro benchmarking. I will go a bit fast because it's what you already did. We already did a lot during this presentation this week now. Yet, when you want to, you find the hotspot. With perf, you find that this function is costing a lot. What is the nice way to proceed? Is to extract this function in a micro benchmark, as Pierre has presented you several times. We presented some micro benchmarks about the things we want to explain. We extract this micro benchmark, make a fake data generator to get some fake data to execute. And then we can work directly on this function to optimize it, look it with some Valgrind, etc. Because this execution will be shorter than the real program execution. Okay, so make your optimization outside of your program. This is most of the time more efficient. Also, I'm using it a lot, getTix. This is coming from a file from FFTW, which is in MIT license. To get, there is a counter, an hardware counter in practice, which is RDTSC, which is incremented at every cycles. So it provides you a clock, which is very efficient to measure some short execution in your program. Okay, so you can measure at the frequency of the CPU directly, the times. So if you want to measure a short execution, you can put getTix at the beginning, getTix at the end, and get a measurement at a cycle, roughly a cycle, cycle per cycle. So let's take an example here. I have my loop for my measurements. I include cycles.h, which I found on FFTW. And I have my for loop. So I say getTix at the beginning. I make my for loop, getTix. My for loop can be short. It can be not 2 cycles. If you want to measure 2 cycles, you will be lost because getTix take a few cycles to make the measurements, but not too much. But if you want to measure something which is 100 cycles or something like this is possible with this counter. And then you can, I like to divide the number of elements I have and to get the cycles per iteration of a loop. Yeah.
Is it declared as volatile, or because I'm mostly worried about out of order execution, and you don't get a representative number.
So normally you need to put some barrier, etc. if you want to be strict. Most of the time, as I'm looking on some loops which take 1,000 something cycles, I'm not caring that it's shifting a few cycles at the beginning or not. If you want to measure something very precise, at some point, yes, you need to put some barrier so the counters are not reordered with the instruction you want to measure. But in practice, you will see that the cost of getTix, of RDTSC, this is an instruction in assembly language in x86 architecture, is taking a few cycles. So you cannot measure one instruction per one instruction. This is not possible. You need to make some average. But what I like with this counter is that when I get the cycles per instruction, I get an information on where I am compared to my architecture, because it's close to what is happening in the architecture. Yes, there is someone saying STD Chrono and NanoBench. Yes, this is in the new C++ standard, one way to access to this counter. Me, sometimes I'm working on some old sessions, so I'm using getTix because it's running everywhere. But true that in the new C++ standard, you can use STD Chrono in some ways with the high frequency clock. There is a parameter to give to use the high frequency clock to use it. Don't try to measure a long time with this, because where I say this just after that, it's incrementing at the speed of the CPU. So it's a 64-bit counter. So of course at 2 GHz, it's falling back to 0 every I don't know 3-4 hours, something like this. So don't try to measure something which take 2 hours. one day with that counter. This is not possible. But to measure something very short, this is very efficient and not perturbating too much the program. This you already seen with Pierre. So the good thing also, I will say it. If you measure with get ticks, you can make one thing is to measure the time of every iteration and make a distribution of it. And sometimes it's showing some things. Here, when I'm plotting the distribution, I see some peaks here, which is the operating system scheduling sometimes. Sometimes the scheduler interrupts the program and schedule it elsewhere. Or sometimes we will show on Friday some effects we can detect thanks to this kind of measurement. So looking at the distribution, when it's normally it should be something like this, a bit not Gaussian, but Gaussian with a long train in the back. If you have several peaks, it says something, and you can try to understand what each peak is to understand what is happening in your code. So this is one way also to sometimes make some measurements. If you have something like this, for example, there is something happening in your code, and you can try to understand. We'll see a bit in more depth one example in Friday when speaking about operating system. So last tool for the last 10 minutes. I'm on time. Cool. The Intel tools. Frankly, to use the hardware counters, this is the most interesting tools because they were very some expert. Historically, this was some expert tools. This hardware counter tools even for Intel. But frankly, from the last 5, 6, or 7 years, Intel has made a lot of efforts to simplify those tools. So now they have a kind of great interface which permits you to understand a bit the counters in a better way because I organized a bit the thing in steps and with a workflow to go deeper and deeper with the counters. So for that, there is two tools, which are Advisor and VTune. Of course, they work only on the Intel processors and not on the AMD one. But they are kind of very good. AMD has also started to develop some tools equivalent, which are not yet at the same level, I think, but they are kind of progressing a lot the past years. So I make one demo just to show quickly the interface. There is Advisor, which is a kind of getting a very large summary of your application, which is done on different domains, memory access, threads, threadings, etc. So you can get what they call some perspectives. You select a perspective about vectorization, about memory, about threading, and you try to focus with the metrics about those aspects of the program. VTune is made more to go more in depth in your program. You can get a performance snapshot, something very widespread. You can get the hotspot, as we did with perf. But then you can get some very deep analysis about memory accesses, threading, microarchitecture. Here you get everything about the hardware counters and going deep in the processor. Okay, I would say this part of the tool is for the experts. This part here, algorithms and parallelisms, is quite accessible for anyone. I will show for the demo only the part on the left because the processor of my laptop is not supported anymore by the tool. So I hope I will not have a demo effect. I will block my virtual machine, otherwise I will have some problems. Pause. And I will move to. So while you install your Intel tools most of the time in your home directory, if it's not provided by your machine, you need to load one MPI set vars. So I'm loading all the Intel environment in my shell, and I can launch Advisor -GUI. So for the first look, I like to pass Advisor first because it's quite simple. It's not providing a lot of things. So maybe I need to make it from scratch. Sorry, I already had something configured. Cancel. Workflows, no. Perspectives, where it is. I want to reset and make a new project. I want to make a new project. Come on. Welcome. Create a project. So I create a project name Grace Scott demo. I need to give where my executable lands. So here I will go in projects, Grace Scott. I already built it. I use you need to use the executable with the -0 so optimized, and debug symbol so it can get access to the source code. So I will take the one compiled with the Intel environment, the Intel compiler, but you can also use the one built with GCC if you want. And I will first measure which one, the -OMP, -S 2000, number of steps, and that's it. And I say, OK. So now I need to choose the perspective I want to look on. So either vectorization or CPU memory roofline. I will discuss a bit more Friday. So we'll go, for example, for the vectorization and code insight. Me, I like to say I, even if it's longer, to get more details on what it can analyze. So I say play. It's running the code. So the output of the code is in the terminal. So if you want to see the progress, you need to come back to your terminal. So it executes the code several times. One just to execute with the hardware counters to make the analysis. And another one with some instrumentation to analyze some things in your code. So this is an execution which is slower in practice. It takes a bit more time. We see here that it's taking a long time to execute. A bit slower, another execution. So if you say I here to get more details, it's making a survey, a characterization, memory access pattern. So making at least 3 executions to get different views on your program. Sorry for the people on the back because I cannot zoom in this. This is a good thing when you make a tool with a web interface, you can zoom. Here I cannot zoom. So sorry if it's small. So here there is a question of Stevenson. Is execution take time in a profile code measure? Is a task take time in a portion of the code measured by the programming tool? How to know if something normal or best we can get out it? Yeah, that's exactly the good question that advisor permit to understand, Stevenson. I will show that advisor is also giving you some hints where you are compared to your CPU performance. So you get the peak performance you can expect. I will show you the chart just after that. So already about the vectorization, it will tell some things. So if I go to the summary, it will say that CPU time is 41 seconds for what I run. There is 2 vectorized loops. So 28 seconds of the execution was done in something which is vectorized. So you can get the same kind of results than with Macao, but in a way which is a bit easier to read in some ways. The loops, they are here. You can get the top loops, the hotspots in practice, saying that if it's vectorized or not, how long it takes, and you can go there to get on the source if you want. And you can click on one loop and get some annotations to say that this loop is vectorized with FMA, etc. Okay, so it's capable also to give you some hints what you can improve on this loop. So here it's already quite nice. You can get code analytics if you want. So here where you have a kind of it's making a point on a graph based on the performance on the machine. So you have the lines. This is a roof line, what we call. I will discuss this again in more depth about memory management on Friday. But you get on this graph the position of your loop, depending on the caches and the DRAM. And you can get some expectation. It's saying that here there is a little amount of thing I can improve in this case because I'm already in the cache. Okay. If the point would have been here, for example, it says that I'm not using the memory efficiently and that I have a lot of things to improve to get the point on the top. Compared to the lines are a bit the limit in terms of memory accesses. Again, I will discuss in more depth this specific chart on Friday. We'll take more time to discuss what it is and how it is running. Because I am out of time now. I just want to show you another thing. So this is a roofline point. So those kind of tools are kind of telling you that you have some margins to improve or not. Don't expect the proposal to be perfect. This is not because you can improve that you will succeed to improve. This is something different. But already you have a kind of an idea if you have some margins. So I hope it answers the questions, Stevenson. So it gives you an estimation of what you can improve, at least in terms of memory accesses and vectorization. So I will not show you now the view in terms of memory insight. Yeah, I can show you. This is exactly where you have the points. On this roofline, I will discuss next talk about memory. I will stop here for advisor, just to go to VTune shortly. So VTune is working relatively the same way, VTune-CV, but showing some different things. I will make a new project just to show. Gray, Scott, same approach, demo. Scoot, ouais, c'est pas grave. My Intel executable. Select. Dash O OMP dash S 2000. And what I forgot. No. So yeah, one of the problems of the Intel tools is that they are kind of following the last processors to work on. So if you have a processor which is too old, from some measurements, they say, you know, this processor is too old, you cannot run on it. My laptop has now 6 years, so it's too old for Intel. But some of the measurements are working. For example, the hotspot part is running well, so I can use it. So I will run. The result is empty, what I did. PMU type, blah, 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 blah. Demo effect. What I did. User, I selected, so here I selected, sorry, I was a bit fast, hotspot on the left here. And why I'm should go. Well, anyway, I will not lose my time because we're out of time. I have already one project which is already open for this. This is not this one. Where I have one. Chess. Yeah. Hotspots. So here it's showing you what are the hotspots. So for example, I'm in OpenMP, so I have a lot of spinning time. My OpenMP is not very efficient on what I did. And we see also in this graph that I'm using most of the time 1 or 2 cores. Okay, so when I have a core, my OpenMP is done in a way which is a bit bad because I'm passing my time to be synchronized. And so the cores are a bit waiting instead of computing in this example. You get the hotspots, which is the unroll sec function we have seen already in the other tools, which is here. I can go directly on this function. And you can see how often it is executed on the threads. So here you get the saturation of the CPU over the time based on the counters. You get the call tree, so you can dig into the call tree to find from where you are coming. Sorry, call tree, bottom up. So kernel unroll sec is coming from was this function here, and you can get all the call stacks to find from where you are coming to reach a point. The last point, which is interesting here, is the flame graph. It's displaying your view as a flame graph, and the larger function is the most of the usage it's taking. So our top function here is our kernel part. So I can select in the stack which part I want to display to zoom for each function, what sub-function has taken the most time. This is quite often, with perf you can get also this flame graph I didn't show you to display in terms of size, to get a view in terms of size, what is the cost of the function relatively to the rest. Threading, you can get some information about the threadings. Here, notably the graph which I was here, and it's saying that I'm using the threadings at 24% only. It's in red, saying that red, this is a problem. It should be green if everything is right. Okay. So I will not enter in all the details. You see that in this tool you get a lot of metrics in practice. Where I am. If I want to run, you can get a lot of details. You can make memory profiling, how much memory your function is using, how much IOs your function is doing, etc. You get a lot of things with some hint every time. Here, probably you can improve something. This is the interest of this tool. It's not only it's giving you some numbers, but giving you some hints that probably you can improve something here. So I will stop here for this presentation because we are out of time. Sorry that you cannot play with those tools by yourself. But this is the problem for the profiling part. It's most of the time you cannot do it anyway. I didn't discuss one thing about profiling. This is about memory management, the mallocs, if you want to profile. We'll discuss that tomorrow with two profilers I'm developing myself, so this time we'll be able to use it everywhere. Malt and NumaProf, two problems about memory management and memory accesses we will discuss tomorrow. Thanks. I don't know if there is some questions remotely or not. Any questions before we stop here? Everything perfect, everyone else on everything, yeah. Okay, end of the journey.
Okay, thank you everyone for attending this day. So a lot of magics, C++ profiling, a lot of stuff. Was a tough day. So tomorrow normally it will be a bit less complex. So Fortran with the same, not maybe the same complexity, but just to show you how to do this kind of optimization with Fortran, and then memory profiling as you were saying. So again, it's really important to your memory. So thanks everyone. Thanks for all the questions, for all the satellite sites, all the people online. Really a pleasure to get all your questions. And have a nice end of the day, and see you tomorrow at 9. And bye.
There is a question. The slides are online already normally.
Yeah, already online. Yeah.